Hello and welcome. Tonight we're going to drift through one of nature's most ethereal phenomena, the northern lights, those curtains of colour that dance across polar skies, turning darkness into something between a dream and a memory. If you enjoyed this journey, consider subscribing to keep these quiet explorations coming your way. Now, let's begin. The Northern Lights carry a name that sounds like it belongs in poetry rather than science: Aurora Borealis. Aurora, the Roman goddess who opened the gates of dawn each morning, her rosy fingers pulling back the curtain of night. Boreas, the Greek god of the north wind, cold and powerful, sweeping down from distant frozen realms. Put them together, and you have a name that captures something essential about these lights. They are celestial, they are northern, and they seem to arrive on some invisible wind that blows between earth and sky. For thousands of years before anyone understood plasma physics or solar wind, people looked up at these lights and saw the divine. The Inuit saw spirits, the Norse saw warriors, the Chinese saw dragons breathing fire across the heavens. Every culture that lived beneath these lights created stories to explain them, and in a sense, all of those stories were correct. Not scientifically, perhaps, but emotionally. Because when you stand beneath an aurora, when green light ripples overhead like water flowing uphill, when curtains of luminescence unfold across half the sky, it does feel like you're witnessing something beyond the ordinary mechanics of the universe. Ancient people called them messages from gods. We call them interactions between solar particles and atmospheric gases. Maybe both descriptions are trying to express the same sense of wonder, just in different languages. The lights themselves exist in a strange middle realm, occurring between 60 and 200 miles above Earth's surface. To put that in perspective, commercial airplanes cruise at about 6 or 7 miles up. The International Space Station orbits at roughly 250 miles. Auroras happen in between, too high for birds, too low for satellites, in a transitional zone where Earth's atmosphere is thinning into the near vacuum of space. It's a peculiar place to exist, this auroral realm. Down where we live, air is thick enough to breathe, to carry sound, to push against your skin. Up where satellites orbit, there's essentially nothing at all, just scattered atoms drifting in darkness. But in that in-between zone, in that twilight region where auroras bloom, the atmosphere is thin enough that individual molecules can travel long distances before colliding with anything else, yet thick enough that when they do collide, when charged particles from the sun slam into oxygen and nitrogen, they release light. It's a Goldilocks altitude, not too thick, not too thin, just right for turning invisible particle impacts into visible colour. You're watching something happen in a place where the definition of atmosphere becomes fuzzy, where Earth and space blur together like watercolours running on wet paper. Every aurora begins its story not here, but 93 million miles away, on the surface of the sun. That's where the particles that will eventually paint our skies with colour first begin their journey. The sun, and that vast sphere of fusing hydrogen, occasionally releases bursts of charged particles, electrons and protons mostly, that stream outward in all directions. Some of them, just by chance, happen to be aimed toward Earth. They travel for 8 minutes across the void, riding the solar wind before arriving at our little blue world. 8 minutes. That's how long it takes light to cross the distance from sun to Earth. Which means that when you watch an aurora, you're seeing the final act of a journey that started less time ago than it takes to brew a pot of coffee. The particles that are exciting oxygen molecules above Alaska right now left the sun more recently than this morning's breakfast. There's something almost intimate about that timeline, despite the cosmic distances involved. The sun sneezes, and 8 minutes later, the Earth's skies light up. We're connected to our star by invisible threads of magnetism and matter, bound together in a relationship that occasionally becomes visible as green and red and purple light dancing across the darkness. In a sense, every aurora is a message sent 93 million miles, written in a language of charged particles, delivered to our atmosphere and translated into colour for anyone willing to look up. The colours you see in an aurora aren't random. They're a kind of signature, a fingerprint left by different gases at different altitudes. Green, the most common auroral colour, comes from oxygen molecules about 60 to 150 miles up. When a charged particle from the solar wind collides with an oxygen molecule at that altitude, it transfers some energy to the oxygen, exciting its electrons to a higher energy state. Then, when those electrons drop back down to their normal state, they release that extra energy as a photon of light, specifically green light with a wavelength of 557.7 nanometers. Red auroras, rarer and often fainter, come from oxygen too, but higher up, above 150 miles where the atmosphere is even thinner. Up there, oxygen atoms can stay in their excited state for minutes rather than fractions of a second, and when they finally release their energy, it emerges as red light at 630 nanometers. It's nature's own colour-coded altitude map, painted across the sky. You can tell how high the particles are penetrating just by looking at the colours. Green means medium altitude, red means high altitude, and if you see blue or purplish tones, much rarer, that's nitrogen getting into the act, molecules that have been ionized or excited at lower altitudes, adding their own wavelengths to the symphony of light. Every colour is a clue, a piece of information about what's happening where, if you know how to read it. The sky becomes a text written in electromagnetic interactions, and we are fortunate enough to find it beautiful. Nitrogen produces its own auroral colours, though you see them less frequently than the oxygen green that dominates most displays. Blue auroras come from nitrogen molecules being ionized, while purplish red comes from neutral nitrogen returning to its ground state. These colours appear mostly at the lower edges of auroral curtains, where the atmosphere is slightly denser and nitrogen is more abundant. But here's something curious. The rarest auroral colours exist at the very edge of human perception, deep violet hues that cameras pick up more easily than our eyes, ultraviolet emissions that we can't see at all without instruments, infrared glows invisible to us but bright to the right detectors. The aurora we experience with our naked eyes is just a slice of the full spectrum, a subset of the light actually being produced. It's like listening to music with earplugs in. You get the general melody, but you're missing overtones and undertones, harmonics above and below your range of hearing. Modern cameras with long exposures and high ISO settings can capture auroral colours and structures that would be invisible to someone standing in the same location, looking at the same sky. Which raises an interesting question. What is the true colour of an aurora? The pale green most people see with their dark adapted eyes. The vivid magenta that appears in photographs. The ultraviolet emissions that human retinas can't detect. Perhaps it's all of those and none. Perhaps the aurora exists across a spectrum broader than any single observer, human or camera, can fully capture. Maybe the complete aurora includes colours we'll never see. For centuries, people who lived beneath the auroral zones reported hearing sounds during intense displays, crackling noises, hissing, sometimes a soft whooshing like wind through trees. Scientists were skeptical. How could something happening 60 miles up produce sound audible at ground level? Sound doesn't travel well through vacuum, and even in the thin air where auroras occur, any noise would dissipate long before reaching the surface. For generations, these reports were dismissed as imagination or wind, or the psychological expectation that something so visually dramatic should produce audible effects. Then, in 2012, researchers confirmed it. Auroras do make sounds, though not in the way anyone expected. The noises aren't coming from the aurora itself 60 miles up. Instead, they're produced much closer to the ground, perhaps only 200 feet overhead, when electromagnetic disturbances from the aurora cause discharges in the inversion layer of the atmosphere. It's a bit like how radio static increases during thunderstorms. The aurora creates electromagnetic conditions that allow charge to build up and suddenly release, producing sharp, crackling sounds. So the witnesses were right all along, and the skeptics were right too. Auroras themselves are silent, as you'd expect from something happening in near vacuum, but they can create conditions that produce sound much closer to Earth, in air thick enough to carry it to your ears. It's a strange, indirect causation. The lights don't make the noise, but the noise wouldn't exist without the lights. And if you're very fortunate, if you're standing outside during a particularly intense auroral display, you might hear that crackling, that hiss, that whisper of electromagnetic forces made audible, nature speaking in a voice at the edge of perception. From the ground, looking up, an aurora appears as curtains or arcs or rays stretching across the sky. But from space, looking down, the view is completely different. Astronauts aboard the International Space Station sometimes drift past their windows and see auroras from above, glowing ovals encircling Earth's magnetic poles like crowns of light draped over the planet. Imagine that perspective for a moment. Instead of standing on a dark plain, looking up at lights dancing overhead, you're floating in the void, looking down at your entire planet wrapped in luminescence. The auroral oval appears as a complete ring, though from any point on the ground you'd only see the portion above your horizon. It's like the difference between standing in a parade and watching from a helicopter. Same event, completely different perception. Astronauts report that auroras from above look more three-dimensional, with clear structure and depth, curtains that stand up from the planet's surface like walls of light. Sometimes they fly through them, passing between glowing tendrils at orbital velocity. And for a few moments the distinction between inside and outside becomes unclear. Are they in the aurora or above it? When does observation become participation? From this vantage point, Earth doesn't look passive. It looks active, engaged in an ongoing interaction with the solar wind, wearing its magnetic field like armour that occasionally lights up where the solar wind strikes it. The planet becomes a character in the story rather than a stage, and the aurora becomes its voice, glowing in the darkness to say, "I am here, I am alive, I am in dialogue with the sun." The Northern Lights have a twin sibling, the Aurora Australis, the Southern Lights, appearing at the opposite end of the planet. When particles from the sun reach Earth, they don't just strike one pole. Our magnetic field funnels them toward both poles simultaneously, creating mirror image light shows in the Arctic and Antarctic at nearly the same time. This is no coincidence. It's geometry. the inevitable result of how magnetic fields work. Earth's magnetic field lines emerge from one pole and curve around the planet to enter at the other pole, forming closed loops through space. When solar wind particles encounter this field, they spiral along these field lines, following the invisible magnetic pathways down toward both poles at once. So if there's an aurora over Norway, there's almost certainly one over Antarctica too, following the same choreography, responding to the same solar stimulus. They're connected, these twins separated by 12,000 miles of planet linked by invisible threads of magnetism. The same particle stream creates both, though few people will ever see both. The Arctic has cities, accessible viewing locations, aurora tourism. Antarctica has penguins and research stations and weather that makes aurora photography a challenge of endurance. But the lights don't care about accessibility. They appear where Earth's geometry dictates, indifferent to whether anyone is watching, painting the Antarctic darkness with the same colours as the Arctic, a reminder that some phenomena are too large to fit within human convenience. Maybe there's something profound in that. Beauty that continues regardless of audience. Light shows performed for empty ice fields and research stations, and the occasional seal hauled out on pack ice, utterly unconcerned with whether anyone appreciates them. The Sami people, indigenous to northern Scandinavia, have lived beneath the northern lights for thousands of years, and their traditional relationship with the aurora was one of respectful caution. You didn't whistle at the lights, didn't mock them, didn't draw their attention. Some legends held that the lights could descend and carry you away if you disrespected them. Others said they were the souls of the departed, and to disturb them would invite misfortune. Whether these beliefs were literally true doesn't diminish their deeper wisdom. The Sami understood something important. These lights represented forces beyond human control. Manifestations of a natural world that didn't exist for human convenience. Approaching them with reverence rather than entitlement made sense, not because the lights had agency or intention, but because maintaining humility in the face of the incomprehensible is generally wise. Our modern science explains the lights in terms of plasma physics and electromagnetic interactions, which is accurate and useful, but perhaps also incomplete, because understanding the mechanism doesn't necessarily capture the experience. You can know exactly why oxygen molecules emit green light at 557.7 nanometers and still feel, standing beneath a full-sky aurora at 3 in the morning, that you're witnessing something that deserves more than mere comprehension. The Sami were quiet under the lights, not because they were ignorant, but because silence felt appropriate, because some experiences called for listening rather than speaking, for receiving rather than analysing. Maybe we should whistle a little less at the universe and watch a little more quietly. The oldest recorded observations of auroras come from China. Nearly 5,000 years ago, Bostwar ancient astronomers described what they called sky candles, or dragons breathing fire across the northern sky. These records, inscribed on oracle bones and later transcribed into historical texts, describe phenomena that match auroral displays: red lights spreading across the horizon, curtains of colour that shifted and moved, luminous clouds that appeared without warning and faded with equal mystery. That these observations happened in China is significant. Most auroras occur in the auroral zones, rings around the magnetic poles typically between 60 and 70 degrees latitude. China lies much farther south, meaning these ancient observers were witnessing auroras during periods of particularly intense solar activity, when the auroral oval expanded far beyond its normal boundaries, The fact that they recorded these events suggests they were rare enough to be noteworthy but frequent enough during active solar periods to develop consistent descriptions. Dragon breath seems like a reasonable metaphor, actually. Auroras do move like living things, writhing and twisting across the sky with serpentine grace. The Chinese observers were working with the vocabulary available to them: dragons, fire, celestial omens, and arrived at descriptions that, while not scientifically precise, capture something true about the experience. Maybe metaphor and measurement are both valid approaches to the same mystery, different tools for different aspects of understanding. The aurora remains fundamentally the same phenomenon whether you call it dragon breath or oxygen emissions. At 557.7 nanometers, I know we've changed our language over 5 millennia, but the lights themselves continue, indifferent to our explanations, performing the same ancient dance between sun and earth that they've executed for billions of years before humans existed to name them anything at all. Benjamin Franklin, in the 1750s, proposed something remarkable for his time: that the northern lights were electrical in nature. This was decades before anyone had a practical electric light, before the word electricity meant much beyond parlor tricks with amber and cat fur. Franklin had been experimenting with lightning, famously flying kites into thunderstorms, beginning to understand that electricity wasn't just a curiosity but a fundamental force of nature. When he turned his attention to auroras, he saw parallels. He was essentially correct, though the full mechanism wouldn't be understood for another 2 centuries. Auroras are indeed electrical phenomena, charged particles interacting with atmospheric gases, creating light through energy transfer. Franklin's insight was extraordinary because he was working almost entirely from intuition and analogy, connecting disparate observations into a coherent theory without the benefit of plasma physics, magnetohydrodynamics, or any understanding of the sun beyond "it's a hot thing in the sky." He couldn't have known about the solar wind, about Earth's magnetosphere, about the complex dance of magnetic reconnection and particle acceleration that creates auroras, but he sensed correctly that the same force that made sparks jump between his Leyden jars was somehow involved in painting the sky with colour. It's a reminder that scientific understanding builds slowly, each generation adding pieces to a puzzle whose full picture only gradually emerges. Franklin provided one piece: it's electrical, and died long before anyone could confirm he was right. The aurora kept its secrets for another 150 years, waiting patiently for human understanding to catch up to human curiosity. The solar wind, that constant stream of particles flowing from the sun, travels at roughly 1 million miles per hour. Let that settle in your mind for a moment. 1 million miles per hour. At that speed, you could circle Earth's equator in about 90 seconds. You could reach the moon in roughly 15 minutes. And yet, crossing the 93 million miles from Sun to Earth takes these particles about 40 hours under typical conditions. Space is incomprehensibly large, and even within our tiny solar system, the solar wind streams outward constantly, expanding into the void in all directions like an invisible exhalation, and Earth just happens to be in the way of a tiny fraction of it. Most of the solar wind misses us entirely, flowing past into the outer solar system and eventually into interstellar space. But the portion that does encounter Earth, that becomes important. That becomes auroras. During particularly fast solar wind events, when coronal mass ejections accelerate particles to higher speeds, the transit time can drop to 15 or 20 hours. These fast streams hit Earth's magnetic field like ocean waves hitting a breakwater, and the results are spectacular. Auroras visible at unusually low latitudes, geomagnetic storms that disrupt satellites and power grids, evidence written in light across the sky that something explosive happened on the sun less than a day ago. We live in the aftermath of solar events, bathed constantly in the sun's outbreath, mostly shielded by our magnetic field, but occasionally, beautifully, reminded that we're embedded in a dynamic system much larger than ourselves. The solar wind connects us to our star in ways both dangerous and magnificent, a 1,000,000-mile-per-hour current in which our planet perpetually swims. Earth's magnetic field acts as a shield, deflecting most solar particles around our planet rather than allowing them to strike the atmosphere directly. If it didn't, if we had no magnetic field, the solar wind would gradually strip away our atmosphere, leaving us as barren as Mars, here which lost most of its magnetic field billions of years ago and subsequently lost most of its air to space. But the shield isn't perfect, and the imperfections are where auroras happen. Near the poles, where magnetic field lines converge and dive back into the planet, the protection weakens. Solar wind particles can follow these field lines down toward the surface, funneling into the polar regions like water spiraling down a drain. It's precisely this weakness that creates the beauty. If Earth's magnetic field were perfectly uniform, perfectly strong everywhere, we might be better protected, but we'd have no auroras. The lights exist because of vulnerability, because of places where the shield is permeable, where the cosmos can touch the atmosphere directly. There is something almost poetic about that. Beauty emerging from imperfection, yet light appearing at the boundaries where protection fails. The auroral zones mark the places where space weather makes contact with Earth, where the barrier between our world and the solar wind becomes thin enough for interaction. They're not flaws in Earth's defenses, exactly. More like intentional gaps, built-in vulnerabilities that allow for exchange, for communication, for the kind of spectacular electromagnetic interaction that paints the sky with colour. Without these weak points, we'd be safer but lonelier, isolated behind an impermeable barrier, never seeing the solar wind made visible, never knowing what we were being protected from. The auroral oval, that ring-shaped region encircling each magnetic pole where auroras most commonly appear, isn't fixed. It expands and contracts depending on solar activity, breathing like a living thing. During quiet periods, the oval might shrink to a tight ring around the pole, visible only from the highest latitudes. But during solar storms, it can expand dramatically, stretching southward in the northern hemisphere, or northward in the southern hemisphere, bringing auroras to places that might go years or decades between sightings. During the most intense geomagnetic storms, the expansion can be extraordinary. Auroras have been seen from the Caribbean, from Mexico, from places within 20 degrees of the equator. The oval doesn't just grow slightly, it blooms, spreading across half a hemisphere, bringing polar phenomena to temperate latitudes, disrupting the normal order of things. People in locations that never see auroras suddenly find their sky painted with unfamiliar colours, a red curtain spreading overhead, and the effect is often unsettling precisely because it's so out of place. The sky isn't supposed to do this here, and yet it does, during those rare occasions when the sun's activity overwhelms Earth's usual protections, when the solar wind pressure becomes strong enough to compress our magnetic field and push the auroral zones far from their normal positions. These expanded auroras are nature's way of announcing, Something significant is happening. The sun is more active than usual. The space environment has changed. They're visible evidence of invisible forces, signs written in light for anyone paying attention. And after the storm passes, the oval gradually contracts again, pulling back toward the poles, returning auroras to their usual haunts, leaving people at lower latitudes with stories of the night the sky turned red, wondering if they'll ever see such a thing again. In September 1859, the most powerful geomagnetic storm ever recorded struck Earth. It's called the Carrington Event, named after the British astronomer Richard Carrington, who observed the solar flare that triggered it. The auroras that night were extraordinary, visible as far south as Hawaii and the Caribbean, bright enough to read by. Brilliant reds and greens spreading across skies that normally never showed such phenomena. But perhaps the strangest detail comes from gold miners in the Rocky Mountains, who reportedly woke up around 1 a.m. thinking dawn had arrived. The auroral light was that bright, that convincing in its mimicry of sunrise, that men sleeping outdoors stirred from their bedrolls and just started making breakfast, began preparing for a day's work, only to gradually realize that the stars were still out, that the light in the eastern sky was moving and shifting in ways that sunrise never does, that they'd been fooled by something altogether stranger than solar dawn. Imagine that confusion, that slow realization that the world wasn't behaving as expected, that the lights overhead weren't heralding day but rather announcing something else entirely, some cosmic event without precedent in their experience. The Carrington Event auroras were bright enough to cast shadows, to make birds sing, to fool human circadian rhythms into thinking night had ended. And this was accompanied by technological mayhem, telegraph systems failing worldwide, operators receiving shocks, paper catching fire from induced currents. The event was a preview of how vulnerable our technological civilization is to solar tantrums, a warning written in beautiful but dangerous light. If a similar storm struck today, estimates suggest it could cause trillions in damage to satellites, power grids, and communication systems. We live beneath a sun that is mostly stable, mostly predictable, but occasionally explosively active, capable of reaching across 93 million miles to remind us that we're not as insulated from cosmic forces as we sometimes imagine. That same 1859 storm didn't just create spectacular auroras, it demonstrated that the lights could have tangible, sometimes dangerous effects on human technology. Telegraph systems across Europe and North America went haywire. Operators reported receiving electric shocks from their equipment. Now, some telegraph lines continued working even after their batteries were disconnected, powered entirely by currents induced by the geomagnetic storm. And in several offices, the electromagnetic pulses were strong enough to set telegraph paper on fire. It's worth pausing on that image. Paper catching fire because of invisible currents induced by auroras. The same phenomenon that creates beauty also creates danger. The same particles that excite oxygen molecules to glow green also induce electrical currents in long conductors like telegraph wires. The auroras are gentle in their direct effects. You can stand beneath them safely, they won't harm you, but their electromagnetic influences can cascade through technological systems in unexpected ways. In 1859, we had relatively little technology to disrupt. Today we have satellites, power grids spanning continents, GPS systems, communication networks, all potentially vulnerable to intense geomagnetic storms. A Carrington-level event today would be catastrophic Not because the auroras themselves are dangerous, but because we've built a civilization that depends on stable electromagnetic conditions, and auroras are evidence that those conditions aren't always stable. The lights mark moments when Earth's electromagnetic environment shifts, when currents flow through the ionosphere and magnetosphere, when the space between ground and sky becomes electrically active in ways our infrastructure wasn't designed to handle. So auroras exist in this strange dual space, beautiful to observe, potentially disruptive to technology, reminders that the universe is both magnificent and indifferent to our conveniences. And during World War I, soldiers huddled in trenches across northern Europe occasionally witnessed auroras bright enough to read by. These displays, often blood red in colour, seemed ominous to men already surrounded by violence, already immersed in a war whose scale and brutality exceeded anything in human history. Imagine being in a trench in France or Belgium, ankle-deep in mud, surrounded by barbed wire and the constant threat of artillery, and looking up to see the sky itself turning red. The timing was coincidental. Solar activity doesn't care about human conflicts, but the psychological impact must have been profound. Red auroras occur when high-altitude oxygen emits light at 630 nanometers, a deep crimson that can spread across the entire sky during intense geomagnetic storms. To pre-scientific minds, these such displays were omens of war or plague. To soldiers in 1917 who had some understanding of auroras but were also exhausted, traumatized, searching for meaning in meaningless slaughter, the red lights must have seemed significant somehow. Some wrote letters home describing the phenomenon, this strange beauty in the midst of horror, evidence that the cosmos continued its processes indifferent to human suffering. The auroras didn't pause for the war. They appeared when solar and terrestrial conditions aligned, painting the sky with colour that happened to match the blood soaking into the mud below. A coincidence of wavelengths and warfare that felt, to witnesses, like it must mean something. Maybe it did, just not in the way they imagined. Maybe the meaning was simply this: even in humanity's darkest moments, even when we're destroying each other with industrial efficiency, the universe continues its ancient patterns, beautiful and terrible and utterly unconcerned with our dramas. The particle collisions that create auroras release tremendous energy, approximately the same total energy as a moderate earthquake, but spread across hundreds or thousands of square miles over the course of hours. It's a diffuse bombardment rather than a concentrated strike. Energy distributed so thinly that we experience it as beauty rather than destruction. Think about that for a moment. An aurora is essentially a gentle catastrophe, a slow-motion explosion playing out over vast regions of the upper atmosphere. Individual particle collisions are tiny, almost insignificant, single electrons hitting single oxygen molecules, me transferring a quantum of energy that gets released moments later as a single photon. But multiply that by trillions of particles, millions of collisions per second, spread across thousands of square miles, sustained for hours, and the total energy becomes staggering. It just arrives so gently, so spread out, that we can stand beneath it safely, watching energy deposition that would be devastating if concentrated into a smaller space or shorter time. It's like the difference between a gentle rain that nourishes crops and a flash flood that destroys them. Same total amount of water, vastly different effects based on how it arrives. Auroras are the universe's way of delivering earthquake-level energy as a light show. transforming violence into beauty through the simple expedient of spreading it out. And we benefit from this dispersal, receiving the spectacle without the destruction, allowed to witness raw power made harmless through distribution, permitted to stand in the middle of a geomagnetic storm and feel nothing but cold air and wonder. Auroras occur on other planets too, governed by the same basic physics, but manifesting in completely alien ways because of different atmospheres, different magnetic fields, different distances from the Sun. Jupiter's auroras, for instance, are hundreds of times more energetic than Earth's, creating permanent glowing rings around both poles, fed not just by the solar wind but by volcanic particles from its moon Io. Imagine that for a moment, a moon's volcanic eruptions creating another planet's light show. Io spews sulfur and oxygen into Jupiter's magnetosphere, and these particles get caught up in Jupiter's powerful magnetic field. They're funneled toward the poles and slammed into the upper atmosphere with such force that the resulting auroras are visible from Earth through modest telescopes. Jupiter's auroras operate continuously, a permanent feature rather than an occasional event, powered by the combination of solar wind and volcanic outgassing from a moon 400,000 miles away. It's a different kind of auroral ecosystem, a reminder that while the physics is universal, the details vary dramatically. Saturn has auroras influenced by particles from its rings. Uranus has auroras that appear sideways because its magnetic field is tilted at a crazy angle. Mars has localized auroras over regions with remnant crustal magnetism, fossils of a global field that died billions of years ago. Every planet with an atmosphere and a magnetic field can potentially have auroras, each one a unique expression of the same fundamental process, charged particles exciting atmospheric gases, but manifested in ways that would look completely alien to someone familiar only with Earth's green curtains. The aurora is a universal phenomenon, a feature of magnetized planets throughout the cosmos, but also deeply local, shaped by the particular circumstances of each world. Saturn's auroras can persist for days, pulsing and shifting like slow-motion breathing, visible in ultraviolet wavelengths that human eyes can't perceive but spacecraft can detect. They're driven partly by the solar wind, like Earth's auroras, but also by Saturn's rotation, which is so fast, roughly 10 hours per rotation, that it creates powerful electrical currents in the planet's magnetosphere. These auroras expand and contract in rhythm with Saturn's rotation, growing brighter and dimmer in a pattern that reflects the planet's internal dynamics more than external solar forcing. It's as if Saturn is creating its own light shows through sheer rotational energy, spinning so fast that it generates auroras almost independently of what the Sun is doing. The effect is hypnotic when you see time-lapse imagery from spacecraft. Oval rings of ultraviolet light pulsing at Saturn's poles, breathing in sync with the planet's 10-hour day, responding to processes in a magnetosphere so vast it could contain dozens of Earths. And these are auroras no human will ever see with naked eyes, existing in wavelengths our retinas don't detect, visible only through instruments. Yeah, light shows performed in colours we can't perceive on a world we'll never stand upon, beneath skies of hydrogen and helium that would kill us instantly. The universe is full of beauty that exists outside human sensory range, phenomena that are real and spectacular, but forever beyond direct human experience, knowable only through the mediation of technology. Saturn's auroras are a kind of secret light show, invisible to us but no less real, pulsing in the darkness of the outer solar system, witnessed only by passing robots we've sent to look on our behalf. Uranus presents perhaps the strangest auroral phenomenon in our solar system. Its magnetic field is tilted 59 degrees from its rotational axis, creating auroras that appear completely sideways compared to what we see on other planets. To understand how bizarre this is, imagine if Earth's magnetic poles were located near the equator instead of near the geographic poles. That's essentially what's happening on Uranus, and the auroras follow this tilted, off-center magnetic field, rather than appearing in neat rings around the rotational poles. As Uranus tumbles through space, and it does literally tumble, rotating on its side like a barrel rolling down a hill, its auroras trace strange, wobbling patterns that shift dramatically over the course of its 17-hour day. Sometimes they appear near the planet's top, if we can even call it that. Sometimes near the side, following magnetic field lines that seem almost randomly oriented from an outside perspective. Scientists studying Uranus's auroras have to account for this bizarre geometry. Trying to understand how auroras behave when the magnetic field doesn't align with the planet's rotation, when the whole system is tilted in a way that defies our Earth-based intuitions. We don't know why Uranus is tilted this way. The leading theory suggests a massive collision early in the planet's history knocked it onto its side, and its magnetic field never recovered a normal alignment. So Uranus's weird auroras are essentially fossils of ancient violence, lingering evidence of some cosmic catastrophe billions of years ago, now manifested as light shows that appear in unexpected places, following rules that seem wrong until you remember that our earthly expectations of normal are just local customs, not universal laws. In 2016, scientists discovered that Earth has invisible proton auroras happening alongside the familiar electron auroras we can see. These proton auroras are created when hydrogen atoms from the solar wind steal electrons and become neutral, allowing them to penetrate deeper into the atmosphere before colliding with oxygen and nitrogen. The resulting light is too faint for human eyes to detect, but instruments can measure it. So there are two auroral light shows happening simultaneously over the polar regions. The visible one we photograph and celebrate, and an invisible one occurring in parallel, detectable only by sensitive equipment. It's like discovering that a concert you've been attending for years actually has an additional soundtrack playing in frequencies beyond human hearing. Both are real, both are happening, but one remains forever hidden from direct perception. The proton auroras add complexity to what we thought was a well-understood phenomenon, reminding us that even processes we've studied for decades still hold surprises, still have layers we haven't fully explored, and it makes you wonder what else is happening that we can't detect. What other invisible processes are occurring in the auroral zones, events in wavelengths or particle types we haven't yet thought to look for? The universe is under no obligation to make itself visible to human senses. We see such a narrow slice of reality, visible light, a fragment of the electromagnetic spectrum, and assume we're seeing everything important. But proton auroras suggest otherwise. They suggest that what we see is just the tip of the phenomenon, the part that happens to overlap with our sensory capabilities, and beneath or beside or around it are other processes, equally real, equally active, forever beyond our direct perception, unless we build tools to extend our senses into those hidden realms. The International Space Station orbits Earth at an altitude of about 250 miles, which means it's occasionally at the same altitude as some auroras, or even lower than the highest auroral emissions. Astronauts have reported the surreal experience of watching auroras at eye level rather than looking up at them, seeing green or red curtains pass by their windows like luminescent fog, flying through light that exists at the boundary between Earth's atmosphere and space. Imagine that shift in perspective. From the ground, auroras are something overhead, something you look up at, something that happens in the sky. But from orbit, the distinction between up and down becomes meaningless, and auroras reveal themselves as three-dimensional structures standing upright from Earth's surface like walls of light. Astronauts describe them as having depth and texture that's impossible to perceive from below, layers and folds and curtains that extend through vertical space, creating corridors and chambers of coloured light. Some have photographed themselves from inside the cupola module, with auroras visible through the windows behind them. Portraits of humans floating in space with electromagnetic light shows happening at their backs. A juxtaposition of biological and geophysical processes that somehow both exist in the same improbable environment. And occasionally, very occasionally, the ISS flies directly through an auroral curtain. During those moments, the astronauts are literally inside an aurora, surrounded by the glow, particles streaming past the station, the same charged particles that are exciting oxygen molecules centimeters outside the hull. They're not just observing the aurora anymore, they're part of it, embedded in the electromagnetic environment that creates it, participants rather than spectators. It lasts only seconds, the station moving at 17,500 miles per hour. But for those seconds, the boundary between observer and observed dissolves completely. Auroras create their own magnetic fields, weak but measurable, as the charged particles move through Earth's atmosphere. Anytime electrical current flows, it generates a magnetic field. That's basic electromagnetic theory. And auroras are essentially vast sheets of electrical current flowing through the ionosphere. These aurora-generated magnetic fields are tiny compared to Earth's main field, but sensitive magnetometers can detect them, can trace the outline of auroral currents by measuring the magnetic perturbations they create. So the lights aren't just passive displays, they're electromagnetically active, temporarily altering the magnetic environment in their vicinity, adding ripples and fluctuations to Earth's magnetic field that persist as long as the aurora does. It's another layer of complexity, another way that auroras are active participants in Earth's electromagnetic system rather than just pretty side effects. The particles create light when they collide with atmospheric gases, and the currents those particles form create magnetic fields that can influence other charged particles, which in turn can affect the aurora itself, creating feedback loops where the aurora modifies its own environment. It's a dynamic, self-interacting system, constantly adjusting and responding to its own presence. And this means that auroras leave signatures in multiple domains. Visible light, obviously, but also magnetic field variations, ionospheric currents, radio emissions, X-rays, infrared radiation. Each one is a different way of perceiving the same underlying phenomenon, a different window into the complex electromagnetic dance happening over the poles. We tend to focus on the visible component because that's what our eyes respond to, but in a sense that's the least important aspect, just the most accessible to human perception. The aurora is primarily an electromagnetic event that happens to produce light as a byproduct. Some auroras move at speeds exceeding 6 million miles per hour, yet the actual gas molecules in the atmosphere barely move at all. What races across the sky isn't the air itself, but a wave of excitation, a pattern propagating through the medium like a ripple, moving across the surface of a pond. The water in the pond stays mostly in place, just bobbing up and down, while the ripple itself travels rapidly outward. Auroras work the same way. A charged particle hits an oxygen molecule, exciting it. That molecule releases a photon and returns to its ground state, but by then, other particles have hit nearby molecules, creating a wave of illumination that sweeps across the sky. Either the individual molecules don't travel, they're essentially stationary, but the pattern of which molecules are excited at any given moment moves at tremendous speed, creating the illusion of motion, the appearance of curtains waving and rippling, when really it's just different molecules lighting up in sequence. It's like a stadium wave at a sports event. The people aren't running around the stadium, they're just standing up and sitting down in their seats. But the wave itself circles the arena at speed. Auroras are nature's stadium wave, patterns of excitation moving through stationary gas, visible evidence of how waves and particles are different categories of existence, how motion doesn't always require physical objects moving. You're watching information propagate, not matter. You're seeing a wave in the excitation field of oxygen molecules, and that wave can move as fast as the causation that creates it, which in some cases means speeds that would cross the continental United States in seconds. The sky becomes a medium for displaying invisible waves, and we're fortunate that the display mechanism is light, something we can see, something that turns electromagnetic mathematics into visual poetry. The sun goes through an 11-year cycle of activity, oscillating between solar minimum, when the sun is relatively quiet, and solar maximum, when it's covered with sunspots and prone to flares and coronal mass ejections. During solar maximum, auroras become more frequent and more intense, visible at lower latitudes, appearing multiple times per week in the auroral zones. During solar minimum, they become rarer, fainter, these confined to higher latitudes, sometimes absent for days or weeks at a time. We're constantly cycling between these states, riding the rhythm of solar activity, experiencing auroral seasons that last years instead of months. The next solar maximum is expected around 2025, meaning we're currently in an active phase, a time when auroras are relatively common, when photographers and aurora tourists have better odds of witnessing displays. But this will pass, as it always does, declining into another minimum around 2030 or so, when the sun's magnetic field will be weaker, sunspots will be rare, and the solar wind will be calmer, and then it will build again, inevitably, following a cycle that has persisted for at least millions of years and probably billions. We don't fully understand why the sun has this 11-year rhythm. We can observe it, measure it, predict it with reasonable accuracy, but the underlying mechanism, why 11 years specifically, why the cycle is sometimes shorter or longer, why solar maximums vary in intensity, remains somewhat mysterious. The sun is following rules we can see but don't entirely comprehend, playing a rhythm we can dance to without quite understanding the musical structure. And we dance anyway, planning aurora trips around the cycle, knowing that our chances are better during some years than others, participants in a cosmic calendar whose origins predate our species and will outlast our civilization. The sun rotates once every 27 days, and if a particularly active region on the solar surface happens to be pointing toward Earth during one rotation, there's a good chance it will still be active 27 days later when it rotates back around to face us again. This creates repeating auroral displays, events that come in 27-day intervals like clockwork, the sun's rotation acting like a lighthouse beam that sweeps past Earth periodically. Auroral forecasters watch for this pattern. If a strong coronal hole or active region produces a nice display, they mark their calendars for 27 days later, knowing there's a reasonable probability of a repeat performance. It's one of the more predictable aspects of space weather, this rotational rhythm that allows the same solar features to influence Earth multiple times across several months. Of course, the active regions themselves evolve, growing and shrinking and sometimes disappearing entirely, so the repetition isn't perfect. But during solar maximum, when the sun is covered with active regions, the 27-day cycle becomes quite pronounced. A pulse that modulates the frequency of auroral displays, a reminder that we're constantly being scanned by the sun's rotation, that different parts of our star take turns facing us, and the aurora we see on any given night depends partly on which slice of the sun happens to be pointing our way. It's like living next to a revolving door that occasionally throws things at you. Most of the time, you're fine. But every 27 days, the same side of the door comes around again, and if that side happens to be particularly volatile, you get another dose of whatever it's emitting. We're remarkably passive in this relationship. We just sit here, orbiting, receiving whatever the sun sends our way, hoping the active regions are pointing elsewhere when they erupt, and grateful when they point at us with just enough intensity to create auroras but not so much as to damage our infrastructure. The most common auroral form is actually the diffuse aurora, a faint shapeless glow without distinct structures or dramatic curtains. These account for the majority of auroral activity, happening almost constantly in the auroral zones, but they're so subtle that they rarely make it into photographs, lacking the visual drama that makes people reach for their cameras. Diffuse auroras are like elevator music for the sky, always present, easily ignored, noticed only when you specifically pay attention. They appear as a gentle brightening of the horizon, a faint wash of green or grey that could easily be mistaken for light pollution or low clouds. Most people who see them don't recognize them as auroras because they don't match the spectacular images that populate tourism brochures and Instagram feeds. But they're real auroras nonetheless, created by the same process as their more dramatic cousins, just fainter, more spread out, less concentrated. They represent the baseline auroral activity, the constant low-level interaction between solar wind and magnetosphere that never fully stops even during solar minimum. And there's something oddly comforting about that, about knowing that the auroral zones are almost never truly dark, that there's always some faint glow happening overhead, some quiet reminder that Earth is embedded in the solar wind, constantly buffeted by particles from the sun, externa, maintaining an ongoing electromagnetic dialogue that occasionally escalates into spectacular displays but never quite falls silent. The diffuse aurora is the whisper that underlies the occasional shout, the quiet hum that persists when the symphony pauses, evidence that the fundamental process is continuous even when the visible manifestation is subtle. Discrete auroras, the dramatic curtains and rays that make for stunning photographs, form along specific magnetic field lines like beads on a string. These are the showstoppers, the displays that make people weep and propose marriage, the ones that seem to dance and flow with apparent intelligence, that create patterns so beautiful they feel intentional, even though they're entirely the product of electromagnetic forces. What makes discrete auroras different from diffuse auroras is concentration. Instead of particles drizzling gently across a wide area, discrete auroras involve focused precipitation of high-energy particles along particular field lines, creating bright arcs or curtains with sharp edges and clear structure. The particles are following Earth's magnetic field, spiraling along invisible lines of force, and where those lines intersect the atmosphere, light appears. So what you're seeing when you watch a discrete aurora is essentially a map of Earth's magnetic field made visible, geometry that's always there but normally imperceptible, revealed temporarily by the accident of particle bombardment. The curtains wave and ripple because the field lines themselves are vibrating, responding to fluctuations in the solar wind, to magnetic reconnection events, to instabilities in the magnetosphere. The aurora isn't moving, the field is, and the aurora is just showing you what the field is doing, like iron filings revealing the shape of a magnet's influence. And this means that auroras are teaching tools, natural demonstrations of electromagnetic physics, if you know how to read them. Every fold in the curtain represents a fluctuation in the magnetic field. Every ray pointing upward is showing you the local direction of a field line. The sky becomes a textbook written in light, and we're fortunate that the lessons are beautiful, even if we don't fully understand what they're teaching. Pulsating auroras flicker on and off over seconds or minutes, synchronized across vast areas of sky in a rhythm that seems almost biological, like the sky is breathing. Scientists only recently discovered that these pulses match fluctuations in Earth's magnetosphere, specifically in regions where waves called chorus are energizing electrons, sending them cascading into the atmosphere in rhythmic bursts. Chorus waves are naturally occurring electromagnetic waves that sound, when converted to audio, eerily like birdsong, rising tones that chirp and warble in the radio spectrum. These waves interact with electrons trapped in Earth's radiation belts, kicking them to higher energies and scattering them into the atmosphere where they create pulsating auroras. So the flickering you see overhead is synchronized with invisible electromagnetic birdsong happening in space, a connection between radio waves and visible light, between processes occurring thousands of miles apart, linked by the physics of wave-particle interactions. The pulsations can cover enormous areas, entire regions of sky brightening and dimming in unison, connected by chorus waves that propagate through the magnetosphere like ripples spreading across a pond. It's another example of how auroras reveal hidden processes, how the visible light is just a tracer for deeper electromagnetic dynamics. The sky pulses because the magnetosphere pulses, because chorus waves are energizing electrons in rhythm, because the whole system is resonating at particular frequencies determined by the size of Earth's magnetic field and the composition of its radiation belts. You're watching a planetary-scale oscillator made visible, a cosmic heartbeat encoded in light, the breathing of a magnetosphere we live inside without usually being aware of its presence. Black auroras are dark patches within bright auroral displays, regions where something temporarily blocks the light-producing mechanism even while the surrounding sky glows brilliantly. They appear as holes in the luminescence, negative spaces, shadows in the glow, and they're among the strangest auroral phenomena precisely because they represent an absence rather than a presence. The physics behind black auroras is still being unravelled, but the leading theory suggests they form where the electromagnetic conditions aren't quite right for particle precipitation. Perhaps the magnetic field has twisted in a way that prevents particles from reaching the atmosphere. Perhaps there's a region where electric fields are pushing particles upward instead of allowing them to fall, whatever the mechanism. The result is darkness, not the darkness of empty sky, but darkness surrounded by light, a void within illumination that moves and shifts as the auroral currents flow around it. It's visually striking when you see it, unsettling in a way that's hard to articulate. Our brains expect either light or darkness, not darkness within light, not shadows that exist without obvious obstacles casting them. Black auroras feel like glitches in reality, places where the expected rules temporarily suspend themselves, and they remind us that auroras are fundamentally about energy flow, about particles reaching specific locations, and when that flow is interrupted or redirected, darkness appears even though the overall system remains active. It's like a river with rocks creating eddies where the current temporarily reverses. Most of the river flows downstream, but in these specific spots the normal pattern breaks down, creating zones that behave differently than their surroundings. The sky becomes a river of light with dark pools scattered through it, evidence that electromagnetic systems can be heterogeneous, that not all regions participate equally in the same process. Steve, a recently identified auroral phenomenon, is a narrow purple ribbon that can stretch thousands of miles across the sky, moving west to east at tremendous velocity. The name started as a joke, a placeholder borrowed from a children's movie, but it stuck even after researchers confirmed this was a genuinely new type of aurora, something that hadn't been documented in scientific literature despite probably existing forever. Steve was discovered by citizen scientists, amateur aurora photographers who noticed this strange purple arc appearing in their images and realized it didn't quite match any officially recognized auroral form. They compared notes online, collected observations from multiple locations, and eventually brought their findings to professional scientists who investigated and confirmed, yes, this is something different. Steve turned out to be a fast-moving river of hot plasma in the ionosphere, a subauroral ion drift channel with temperatures reaching thousands of degrees Fahrenheit, visible as a purple glow when atmospheric gases interact with the flowing charged particles. Now, it's accompanied sometimes by green picket fence structures that were eventually named, somewhat less whimsically, Steve's Picket Fence, though the physics of those remains even less understood. The whole discovery is a reminder that auroral science isn't finished, that despite centuries of observation we're still finding new phenomena, still encountering patterns we hadn't previously recognized, and it's a reminder that science benefits from the broader community, from people who pay attention to details, who notice when something doesn't quite fit existing categories, who care enough to document and share their observations. Steve existed long before we named it, appeared in skies over generations of humans who looked up and saw purple light without quite knowing what to call it. But it wasn't scientifically recognized until amateurs with digital cameras and internet connections decided to figure out what they were seeing. The temperature in the auroral zone can reach thousands of degrees Fahrenheit during intense displays, individual gas molecules moving at speeds that translate to extreme heat by thermodynamic definitions. And yet, paradoxically, you would freeze to death if you were somehow transported there, because the air is so thin that temperature loses its usual meaning. Temperature is fundamentally about the average kinetic energy of particles, how fast they're moving, how hard they'd hit you if you collided with them. In the auroral zone, individual molecules are moving very fast, energized by particle collisions, vibrating and tumbling at speeds that correspond to high temperatures. But there are so few molecules per cubic meter that you'd barely interact with any of them. It's like the difference between standing in a room with a single bullet flying past you versus standing in a hailstorm. The bullet has more energy than any individual hailstone, but the hailstorm will hurt more because there are so many hailstones hitting you. In the auroral zone, the bullets are fast but sparse. You'd lose heat through radiation faster than you could gain it from collisions with hot molecules, and you'd freeze in the vacuum while simultaneously being surrounded by air technically hot enough to boil water. It's a strange inversion, a reminder that temperature is a macroscopic concept that becomes weird and almost meaningless when you're dealing with near vacuum. The auroras glow in an environment that's both scorching and freezing, where heat and cold exist simultaneously, depending on how you measure them, where individual molecules race at thermal extremes, while the bulk environment remains lethally cold for any biological entity. Physics becomes counterintuitive at the boundaries, in transitional zones, in places where Earth's atmosphere gradually fades into space. Auroras were likely much more common in Earth's early history, billions of years ago when our planet's magnetic field was weaker and more variable. The young Earth, still settling into its current geological patterns, probably had a magnetic field that fluctuated more wildly, that didn't provide the same stable protection we enjoy today, and this would have meant more frequent and more widespread auroral displays. Imagine a younger Earth with nightly light shows visible from nearly every latitude, a world where the sky regularly turned green or red, where auroras were as common as clouds, where any location on the planet might witness them on any given night. Of course, there was no one to watch them back then. Life was still single-celled, confined to oceans, completely unaware that the sky existed, let alone that it was putting on spectacular displays. The most beautiful light shows in Earth's history played to an audience of bacteria and rocks, witnessed by nothing capable of appreciating them, beauty occurring without observers, without meaning, without anyone to care, and this continued for billions of years, gradually declining as Earth's magnetic field strengthened and stabilized, the auroral ovals contracting toward the poles, the frequency decreasing, until by the time humans evolved and started looking up at the sky, auroras had become a polar phenomenon, rare at lower latitudes, special rather than mundane. We're living in an era of relatively stable geomagnetism, in the tail end of a long process of planetary maturation, and the auroras we see are remnants, echoes of what was once much more common. Perhaps in the far future, if Earth's magnetic field continues to strengthen, auroras will become even rarer, even more confined, until eventually they might disappear entirely, and whatever intelligent beings exist then will look up at dark polar skies and never know that once, long ago, this planet was wrapped in light. The oldest known representation of the Northern Lights might be a 30,000-year-old cave painting in France, showing what some researchers interpret as an auroral display. The painting depicts arcs and rays of colour spreading across what appears to be a sky, patterns that match auroral forms, rendered in ochre and charcoal by Paleolithic artists who had no concept of plasma physics or solar wind, but who clearly saw something remarkable enough to record on cave walls. Of course, the interpretation is debated. It always is with prehistoric art. Maybe it's an aurora, maybe it's abstract symbolism, maybe it's a representation of something else entirely, some vision or spiritual experience or artistic expression that has nothing to do with actual sky phenomena. We'll never know for certain what the artist intended, what they were trying to capture or communicate, but the possibility remains that our Paleolithic ancestors, not huddled in caves during the last ice age, occasionally witnessed auroras bright enough to be visible from southern France, displays that occurred during intense solar storms when the auroral oval expanded far from its normal boundaries. And if they looked up and saw green and red light painting the sky, they would have had no framework for understanding it, no scientific explanation, no concept of Earth's magnetic field or charged particles or atmospheric gases. They would have experienced it as pure phenomenon, unexplained and perhaps unexplainable, beauty or terror or wonder or all of those together, something significant enough to record for future generations, even if they couldn't explain what it was. We're looking at the same phenomenon they saw, separated by 30,000 years and an entire scientific revolution. And we understand the mechanism, but perhaps not the experience. The raw impact of seeing the sky do something impossible, something that violates everyday expectations of how the world works. Maybe our scientific understanding enriches the experience, or maybe it diminishes it slightly, or maybe it does both, giving us comprehension at the cost of mystery. Norse legends held that the northern lights were reflections from the shields and armour of the Valkyries, warrior maidens who rode across the sky collecting fallen heroes to bring them to Valhalla. The lights would shimmer and dance, metallic gleams in the darkness, and to Norse warriors this explained both the visual phenomenon and gave it meaning. The lights marked the presence of divine choosers of the slain, celestial beings involved in sorting worthy warriors from common dead. It's a beautiful explanation, really, even if it's not scientifically accurate. The lights do move like cavalry crossing the sky, do shimmer like polished metal, do appear suddenly and dramatically like supernatural intervention. And for a culture that valued martial prowess, that saw death in battle as the highest achievement, that believed the afterlife was a great hall where warriors feasted eternally, the idea that the lights marked the Valkyries' passage made emotional sense. The cosmos was participating in human drama, acknowledging the significance of warfare, providing visible evidence that the gods cared about battle outcomes. Of course, the lights appeared whether battles were happening or not, but that could be explained. Perhaps the Valkyries were practicing or travelling to distant conflicts, now or gathering heroes from battles in other lands. The framework was flexible enough to accommodate observations while maintaining its core narrative. And this is how humans have always worked, building explanatory frameworks that make sense within our cultural contexts, that give meaning to phenomena we don't fully understand. We've replaced Valkyries with plasma physics, but the impulse is the same. We can't tolerate unexplained phenomena, can't just accept that things happen for no reason we can discern. So we build explanations, whether mythological or scientific, stories that connect observations to larger frameworks, that give us the illusion of understanding even when the mystery remains fundamentally intact. Finnish folklore claimed auroras were caused by a firefox running across the Arctic fells, its tail sweeping sparks into the sky as it ran. The Finnish word for aurora, revontule, literally translates to foxfires, preserving this ancient explanation in the modern language, even though everyone now knows the actual mechanism involves solar wind and magnetic fields rather than supernatural canines. There's something charming about this explanation, something that captures the playful, dancing quality of auroral motion better than scientific descriptions of magneto-hydrodynamic instabilities. A fox's tail sweeping sparks, you can almost see it, can almost imagine the aurora as fur-like wisps of light tracing invisible movement, following the path of something quick and clever and impossible to catch. The fox in Finnish mythology was a trickster figure, associated with cunning and magic, so having it create these mysterious lights made sense within the cultural logic, and unlike some mythological explanations that assign dark or ominous meanings to auroras, the firefox story is relatively benign, even whimsical. The lights aren't warnings or omens, they're just the side effect of a magical fox going about its business, creating beauty as a byproduct of its passage through the landscape. Modern Finns still use revontule, still call the lights foxfires, even while understanding the science, maintaining linguistic connection to the old story while accepting the new explanation. Language preserves beliefs long after the beliefs themselves have been abandoned, carries forward the poetry of old explanations into new contexts, allows us to hold multiple frameworks simultaneously. So you can know about plasma physics and still appreciate the image of a fox sweeping sparks into the sky, can hold scientific and mythological explanations in your mind without conflict, understanding that both are attempts to make sense of beauty, even if only one accurately describes the mechanism. Medieval Europeans sometimes interpreted red auroras as omens of war or plague, especially during times of crisis. When the sky turned blood red, when crimson light spread across the heavens, it seemed apocalyptic to people who had no scientific framework for understanding the phenomenon, who were already living through violence or disease or famine and looking for signs that would give meaning to their suffering. It's easy to see why blood-red lights would seem ominous. Red auroras are relatively rare, requiring specific conditions, high-altitude oxygen emissions, usually during intense geomagnetic storms. They spread across the entire sky sometimes, turning night into something resembling perpetual sunset, bathing the landscape in crimson light that makes shadows appear strange and elongated. To medieval minds steeped in religious symbolism, where red signified blood and martyrdom and divine judgment, such displays would naturally seem significant, messages written in the sky by forces beyond human comprehension. And the fact that red auroras often appeared during periods of high solar activity, which also sometimes coincided with climate fluctuations that affected crop yields and disease patterns, would have reinforced the association. The aurora didn't cause the wars or plagues, but it appeared during the same periods, creating a correlation that felt like causation, encouraging the belief that celestial and terrestrial events were linked. We now understand that solar activity affects Earth's climate in subtle ways, that the sun's variability can influence atmospheric patterns, so medieval observers weren't entirely wrong to connect sky phenomena with earthly troubles. They just drew the wrong kind of connection, assigning intentionality and omen reading to what were actually complex but mechanistic interactions between solar output and terrestrial systems. The sky wasn't warning them. It was just responding to the same solar conditions that were indirectly affecting their weather and agriculture. But distinguishing correlation from causation is difficult enough today with all our statistical tools. For medieval peasants watching red light spread across the sky while plague ravaged their village, the connection must have seemed obvious and terrifying. The Inuit had many explanations for auroras, varying between different groups and regions. Some believed the lights were spirits of the dead playing ball with a walrus skull, the aurora being the light that escaped as the skull was kicked back and forth across the sky. Others thought the lights were torches held by spirits guiding recently deceased souls to the afterlife, a cosmic escort service helping the dead navigate from Earth to whatever came next. Both explanations share a common theme. The lights are connected to death, to the realm of ancestors, to forces beyond mortal life. This makes sense for a culture living in the Arctic, where survival was precarious, where death was present and familiar, where the boundary between living and deceased felt thinner than in more comfortable climates. The auroras appeared most often during winter, the season of darkness and cold and heightened mortality, so connecting them to death and spirits had an intuitive logic. And there's something comforting about the Escort explanation, the idea that the lights represent guidance for the dead, that souls don't wander lost but are actively helped along their journey by luminous beings carrying torches. It transforms what could be a frightening phenomenon into a benevolent one, evidence that the cosmos cares for the dead, that the passage from life to whatever comes after is attended and witnessed and illuminated. The walrus skull story is stranger, more playful, suggesting that the afterlife includes games, yet that spirits retain enough personality and energy to engage in sports, that death isn't the end of activity but just a transition to a different kind of existence, where celestial ball games are possible. Both stories, whether comforting or playful, do the same work. They integrate the aurora into the cultural worldview, make it meaningful within existing frameworks of understanding, transform unexplained light into evidence of spiritual realities that the Inuit already believed in. The lights weren't alien or inexplicable. They were confirmations of what people already knew, visible proof of invisible truths. Auroras produce X-rays, a discovery made only in 2001 when scientists finally had sensitive enough instruments to detect them. These are high-energy photons created when the most energetic electrons from the solar wind collide with atmospheric gases, transferring enough energy to excite not just visible light emissions but X-rays as well. The X-ray aurora is invisible to human eyes, undetectable without specialized equipment, but it's there nonetheless, adding an invisible component to the visible spectacle. The X-rays are weak, nothing like what you'd encounter in a medical imaging device, not dangerous to anyone on the ground or even to astronauts in orbit. But they're real, part of the full electromagnetic spectrum of auroral emissions, evidence that the phenomenon extends beyond what we can see. And this raises the question, what else are auroras producing that we haven't detected yet? We've found visible light, ultraviolet, infrared, radio emissions, X-rays. What about gamma rays? What about particle emissions we don't have names for? Every time we point a new instrument at the aurora, we discover something we didn't know was there, some additional layer of complexity, some wavelength or particle type that was happening all along but remained invisible until we developed the technology to detect it. It's humbling, this constant expansion of what we know about phenomena we thought we understood. Auroras have been studied scientifically for centuries, photographed extensively, measured from ground and space, modelled in computer simulations, and yet they keep revealing new aspects, keep demonstrating that our understanding remains incomplete. Maybe we'll never have a complete picture. Maybe there are aspects of auroral physics that will remain undetectable with any technology we can imagine, processes occurring in regimes we can't access, phenomena that exist but leave no signature we can measure. The X-ray discovery suggests that auroras are larger than we perceive, that the visible display is just the part that happens to overlap with human sensory capabilities, and around it, above and below and beside it, are other emanations in wavelengths both longer and shorter, a full spectrum phenomenon of which we see only a fragment. The auroral electrojet, A powerful electrical current flowing through the auroral zone can exceed 1 million amperes during intense geomagnetic storms. To put that in perspective, a typical household circuit breaker trips at 15 or 20 amperes. The current flowing through the ionosphere during a major aurora is roughly 50,000 times larger than what powers your refrigerator, spreading across hundreds or thousands of miles, invisible but electromagnetically potent. This current doesn't flow through wires or any physical conductor in the traditional sense. It flows through plasma, through ionized gas in the upper atmosphere, electrons and ions drifting in opposite directions to create a net movement of charge. And because it's so powerful, it induces secondary currents in anything conductive on the ground. Power lines, pipelines, railroad tracks, even the Earth itself. During the 1989 Quebec blackout, auroral currents induced surges in the power grid that tripped circuit breakers and transformer protections, it cascading into a complete system failure that left 6 million people without electricity for 9 hours. The aurora itself was beautiful that night, visible as far south as Texas, but its electromagnetic influence was causing havoc in infrastructure hundreds of miles away. It's a reminder that auroras aren't just passive light shows, they're active electromagnetic events, currents flowing through the sky that can reach down and touch our technology, that can make compasses spin wildly, that can interfere with radio communications, that can induce voltages in long conductors sufficient to damage equipment or even start fires. The lights are beautiful, but they're also powerful, evidence of energies that dwarf human scale, processes that make our electrical systems look fragile and temporary by comparison. We've built a technological civilization that depends on stable electromagnetic conditions, and auroras are polite reminders that those conditions aren't always stable, that we live on a planet embedded in a dynamic electromagnetic environment that occasionally flexes its muscles. Oil pipelines in Alaska have to be specially designed to handle the electrical currents induced by auroral activity. Without proper insulation and grounding, these pipelines, which stretch for hundreds of miles through the auroral zone, would act like enormous antennas, picking up electromagnetic fluctuations from auroras and converting them into electrical currents flowing through the steel. Over time, these currents would cause rapid corrosion, eating away at the metal from the inside, weakening joints and seams, potentially causing catastrophic failures. Engineers designing Arctic infrastructure have to account for space weather in ways that engineers working at lower latitudes never consider. They install electrical isolation at regular intervals, breaking the pipeline into electromagnetically separate sections so currents can't build up across long distances. They add cathodic protection systems that counteract the corrosion-inducing effects of stray currents. They monitor the electromagnetic environment constantly, measuring ground currents and auroral activity, adjusting protective systems in response to changing conditions. It's infrastructure engineering that extends into space weather forecasting, a merger of disciplines that wouldn't be necessary if Earth's electromagnetic environment were perfectly stable. The pipeline engineers aren't thinking about the beauty of auroras, they're thinking about corrosion rates and failure probabilities and maintenance schedules. But they're solving problems created by the same phenomenon that draws tourists northward, the same particle precipitation that creates green curtains in the sky. The aurora is simultaneously an attraction and an engineering challenge, something to photograph and something to defend against, beauty and hazard coexisting in the same electromagnetic package. And this duality extends to almost everything about auroras. They're scientifically fascinating but technologically disruptive, visually spectacular but potentially dangerous, evidence of processes both creative and destructive occurring simultaneously in the thin air above the poles. Homing pigeons can become disoriented during auroral storms because these events disrupt Earth's magnetic field, temporarily shifting and warping the invisible lines that the birds use for navigation. Pigeons have magnetoreception, the ability to sense magnetic fields, probably through magnetite crystals in their beaks or through quantum effects in certain proteins in their eyes. Regardless of the exact mechanism, they navigate by following magnetic field lines, using Earth's field as a kind of invisible map that guides them home across hundreds of miles. But during intense auroral activity, that map becomes unreliable. The magnetic field lines shift, fluctuating in response to the currents flowing through the ionosphere. What was north-northeast might temporarily point more eastward. What was a smooth gradient might develop wrinkles and perturbations. The pigeon's navigational system evolved over millions of years to work with a relatively stable magnetic field, suddenly encounters conditions outside its normal operational parameters. Some birds compensate, using visual landmarks or the sun's position or other cues. Others become genuinely lost, circling in confusion, unable to reconcile what their magnetic sense is telling them with what they expect. It's a reminder that many organisms besides humans depend on stable electromagnetic conditions, that Earth's magnetic field is part of the environment in ways we rarely consider because we can't sense it directly. We've built compasses and magnetometers to detect magnetic fields, but many species have those instruments built in, or inherited from ancestors who evolved magnetic sensitivity long before humans existed. And when auroras disrupt the field, when space weather makes the invisible map unreliable, creatures that depend on that map suffer the consequences. We're not the only ones affected by solar activity, not the only species trying to navigate a world whose electromagnetic foundation occasionally shifts beneath us. Auroras can affect satellite electronics, causing what engineers call single-event upsets, where energetic particles flip individual bits in computer memory. A single charged particle from the solar wind, accelerated to high energy by auroral processes, strikes a memory chip aboard a satellite. The particle's energy is sufficient to change a 0 to a 1 or vice versa, corrupting data, potentially causing errors in calculations, sometimes triggering unexpected behavior. Most satellites are designed with radiation hardening and error correction systems to handle this. Memory is redundant, calculations are checked against backups, critical systems have watchdogs that detect anomalous behavior and trigger resets. But occasionally, a particle strikes at just the wrong moment, flips a bit that matters, and the satellite glitches. It might reboot unexpectedly, switching to backup systems, interrupting communications for a few seconds or minutes. Usually it recovers automatically, resumes normal operations, logs the event as a radiation-induced upset. The satellite isn't broken. It was just temporarily confused by electromagnetic conditions, nudged into an error state by a single particle that happened to hit a sensitive location. And the satellite operators on the ground see the telemetry anomaly, correlate it with auroral activity, make a note, and continue. It's routine, part of operating spacecraft in an environment that's not truly empty, that contains radiation and particles and electromagnetic fields that can reach through shielding and touch the delicate electronics inside. Auroras mark periods of increased risk, times when the radiation environment becomes more hazardous, when the probability of bit flips and system upsets increases. Satellite operators watch space weather forecasts the way airlines watch storm forecasts, planning around predicted disturbances, taking precautions when the auroral indices spike, hoping their radiation shielding and error correction prove sufficient to handle whatever the magnetosphere throws at them. The total energy of a large auroral display is comparable to a magnitude 5.5 earthquake, but distributed over hours and thousands of square miles instead of concentrated into seconds in a localized epicenter. It's roughly the same total amount of energy, somewhere in the range of 10 to the 14th power joules, but the way it arrives makes all the difference between catastrophe and beauty. An earthquake releases that energy as seismic waves that shake buildings and crack pavement and topple structures, all the violence arriving in less than a minute, concentrated in a region small enough that the intensity can be devastating. An aurora releases the same energy as heat and light spread across the entire auroral zone over the course of hours, so thinly distributed that you can stand beneath it without feeling anything but cold air and wonder. It's a lesson in how distribution transforms experience. The same total energy, delivered differently, creates entirely different phenomena. If you could somehow concentrate an aurora's energy into a smaller volume and shorter time, it would be destructive. If you could spread an earthquake's energy across thousands of miles and several hours, it would be barely noticeable. The universe is indifferent to these distinctions. Energy is energy, joules are joules. But from a human perspective, the difference is everything. We build monuments to survive earthquakes and tourism industries around auroras, even though they're energetically equivalent events. The aurora is a gentle giant, a slow-motion explosion, violence made beautiful through the simple expedient of spreading it out, of taking what could be destructive and distributing it so thinly that it becomes art instead of disaster. And maybe there's a larger lesson there about intensity versus magnitude, about how the same underlying reality can manifest in radically different ways depending on timescale and spatial distribution, about how focusing and dispersing are transformations as profound as creation and destruction. Auroral light is extremely efficient, converting particle energy directly into photons with minimal waste heat. When an electron from the solar wind collides with an oxygen molecule, exciting it to a higher energy state, and that molecule then releases a photon as it returns to ground state, almost all of the transferred energy becomes light. There's very little lost to heat or other processes. It's nearly perfect conversion of kinetic energy to electromagnetic radiation. If we could replicate this efficiency in artificial lighting, we'd revolutionize energy consumption worldwide. Current LED technology is maybe 40 to 50% efficient at best, converting roughly half of electrical input into visible light and wasting the rest as heat. Incandescent bulbs are far worse, maybe 5% efficient, basically small heaters that produce light as a side effect. But auroras achieve efficiencies that approach theoretical limits, doing naturally what engineers struggle to accomplish with sophisticated technology. Of course, we can't easily replicate the conditions. Auroras operate in near vacuum at altitudes where the atmosphere is too thin to breathe, so using excitation mechanisms that require particle accelerators or similar equipment to reproduce. But the principle remains tantalizing. Nature has solved the problem of efficient light generation, demonstrates it nightly over the poles, shows us that converting energy to light without significant waste is physically possible. We just haven't figured out how to do it in practical, room temperature, atmospheric pressure conditions. The aurora is like a proof of concept, evidence that the laws of physics permit extremely efficient light generation, even if the engineering challenges of applying those principles in useful ways remain formidable. And so the lights continue, demonstrating perfect efficiency to no particular audience, converting solar wind energy to photons with a proficiency that makes our best technology look crude, unconcerned that we're watching and learning but still unable to match their performance. The typical aurora produces only about as much light as the full moon spread across a large area. This surprises people who've seen photographs of vivid green curtains that look bright enough to read by. The discrepancy comes from camera capabilities. Long exposures and high ISO settings can gather light over seconds or minutes, accumulating photons until the image appears far brighter than what the human eye perceives in real time. What makes auroras visually dramatic isn't raw brightness, but contrast and movement. They're relatively faint in absolute terms, but they appear against a dark sky, and they move, and they have structure and colour, and these qualities combine to create an impression of intensity that exceeds the actual light output. You stand beneath a strong aurora, and you might be able to see your shadow faintly, might notice enough illumination to navigate without a flashlight, but you won't be reading books by auroral light unless the display is truly exceptional. Most auroras are more whisper than shout in terms of illumination, adding perhaps 1 or 2% to the ambient light level, enough to notice but not enough to fundamentally change the darkness. And this gentleness is part of their appeal, actually. They're not overwhelming. They don't blind you or wash out the stars. They exist in a sweet spot of visibility, bright enough to see clearly, faint enough to maintain the night's essential character, present without dominating. Photographs lie about this, or at least exaggerate, capturing colours and intensities that exceed what most people will ever see with naked eyes, which creates a strange situation where many first-time aurora viewers feel slightly disappointed, because reality doesn't match the images they've seen, because their eyes can't gather light the way a camera sensor can, because the universe as directly perceived is always fainter than the universe as photographically mediated. But maybe there's value in that faintness, in the subtlety, in aurora that requires dark adaptation and attention, that rewards patient watching rather than shouting for immediate notice. Extremely rare, all-red auroras occur when solar particles penetrate deeper into the atmosphere than usual, exciting oxygen at lower altitudes where different emission mechanisms dominate. These displays can turn the entire sky crimson, a deep blood red that spreads from horizon to horizon, eliminating all other colours, transforming night into something that resembles neither day nor normal darkness, but some third state altogether. All red auroras are so rare that many professional auroral researchers have never seen one. They require specific conditions, very high energy particles able to penetrate deep into the atmosphere, usually during extreme geomagnetic storms. When they do occur, the effect is unsettling in ways that green auroras aren't. Green feels natural, familiar, close enough to bioluminescence or phosphorescence that our brains can categorize it as unusual but not threatening. Red feels wrong, especially when it's everywhere, when the entire visible sky has turned the color of blood or fire, when shadows appear in tones no one has seen before. The ancient observers who witnessed all red auroras without scientific context must have been terrified. The sky turning red was a sign of apocalypse in many religious traditions, evidence that the world was ending or that divine judgment was imminent, and you can hardly blame them for that interpretation. When the fundamental colour of night changes, when darkness becomes crimson, when the visual environment shifts into something outside all previous experience, apocalyptic explanations seem reasonable. We now understand that all red auroras are just physics, just particle precipitation at unusual energies, no more inherently meaningful than green auroras, but the visceral impact remains. Something in human neurology reacts strongly to all red light, finds it disturbing or ominous. This is perhaps because it triggers associations with blood and fire and danger. The universe doesn't care about our psychological responses, produces all red auroras according to electromagnetic principles that have nothing to do with human comfort, but we experience them through nervous systems evolved to find red en masse threatening, and no amount of scientific understanding completely overrides that instinctive response. Auroras are more common during equinoxes, March and September. Due to the geometry of Earth's magnetic field relative to the solar wind. This is called the Russell-McFerran effect, and it describes how the orientation of Earth's tilted magnetic field makes it more vulnerable to solar wind coupling during the transition seasons between summer and winter. The effect is subtle, but statistically significant. If you plot auroral frequency across the year, you see peaks in March to April and September to October, dips in June to July and December to January. The difference isn't dramatic. Auroras can occur any time of year, but the probabilities shift depending on season, on where Earth is in its orbit, on how its magnetic field is oriented relative to the incoming solar wind. It's another reminder that auroras depend on geometry as much as energy, that the alignment of invisible magnetic structures matters as much as the intensity of particle flux. Earth's magnetic field doesn't point straight up relative to its orbital plane. It's tilted, skewed, and as Earth orbits the Sun, this tilted field rotates through different orientations relative to the solar wind flow. During equinoxes, the orientation happens to be particularly favourable for magnetic reconnection, for the solar wind's magnetic field to couple efficiently with Earth's field, allowing more particles to enter the magnetosphere and eventually precipitate into the atmosphere. It's celestial geometry determining auroral probability, angles in space translating to frequencies of light shows on the ground. And if you're planning an aurora trip, if you want to maximise your odds, this matters. Late March or late September, other factors being equal, give you better probabilities than June or December. The effect isn't large enough to override solar activity. A strong geomagnetic storm in December will produce better auroras than a quiet period in September, but on average, across many years, the equinoxes favour aurora watchers through nothing more than the accident of how Earth's magnetic field happens to be oriented. Scientists can predict auroral activity about 30 to 60 minutes in advance by monitoring solar wind conditions at satellites positioned between Earth and the Sun, specifically at a point called L1, about 1 million miles from Earth. These satellites, like the Advanced Composition Explorer, ACE, or the Deep Space Climate Observatory, DSCOVR, sit at a gravitationally stable point where they can measure incoming solar wind and send warnings back to Earth before that same solar wind arrives. It's a remarkably short prediction window, barely enough time to drive to a dark viewing location or set up camera equipment, but it's better than no warning at all. The satellites measure solar wind speed, density, there's a magnetic field orientation, and other parameters that determine how strongly the solar wind will interact with Earth's magnetosphere. When they detect fast, dense solar wind with a southward-pointing magnetic field, the ideal conditions for aurora generation. They send alerts, and scientists can say with reasonable confidence, auroras are likely in the next hour, probably at these latitudes. Expect moderate to strong activity. And then people wait, watching the sky, hoping the prediction is accurate, knowing that even with all our monitoring and modelling, auroras remain somewhat unpredictable in their details. The large-scale patterns are forecastable, but the exact timing, the specific forms, the colours and intensities, those remain uncertain until the aurora actually appears. There's something both modern and ancient about setting an alarm to wake you for a predicted light show, about using satellites and computer models to forecast something that our ancestors could only wait and hope to witness, about combining scientific prediction with the essential passivity of aurora watching. You can forecast them, but you can't control them, can't make them appear or intensify or persist. You can only watch, waiting for the cosmos to perform on its own schedule, grateful that at least now you have half an hour's warning instead of none. The auroral zone, the ring around each pole where auroras are most common, is typically centered about 10 to 20 degrees away from the geographic pole, offset because Earth's magnetic poles don't align perfectly with its rotational poles. The magnetic North Pole currently sits in the Canadian Arctic, hundreds of miles from the geographic North Pole, and it's constantly moving, drifting northward at speeds that have recently accelerated to about 30 miles per year. This offset creates an asymmetric pattern of auroral activity. Some locations at similar latitudes see auroras much more frequently than others, simply because they sit closer to the magnetic pole, closer to where field lines funnel solar wind particles into the atmosphere. Fairbanks, Alaska is a famous aurora destination partly because it sits almost directly beneath the auroral oval's typical position. Scandinavia's northern coast benefits from a similar geometric fortune, but there are places at the same latitude that rarely see auroras because they're farther from the magnetic pole and are sitting outside the usual boundaries of the oval. And as the magnetic pole continues its wandering, a process that's normal, that's happened throughout Earth's history, but that's currently proceeding faster than usual for reasons we don't fully understand, the auroral zone shifts with it. The best viewing locations are gradually changing, degree by degree, year by year, tracking the magnetic pole's migration. Perhaps in a few decades, currently optimal locations will be slightly less optimal, and new spots will emerge as better viewing sites. The aurora is faithful to magnetism, not geography, following invisible field lines wherever they happen to lead, indifferent to human infrastructure and tourism investments, painting the sky wherever the geometry dictates regardless of whether anyone has built hotels and viewing platforms there. And during extreme solar storms, the auroral zones can expand to cover half of Earth's surface, bringing displays to latitudes that might not have seen them in decades or centuries. The expansion isn't gradual, it can happen in minutes, the auroral oval suddenly ballooning outward as solar wind pressure intensifies, as the magnetosphere compresses, as the normal boundaries between protected and exposed regions shift dramatically. These rare events transform the aurora from a polar phenomenon into a global one, visible from places where it becomes news, where people who've never seen such lights flood emergency services with reports of strange glows in the sky, where the unexpected intrusion of space weather into everyday life causes confusion and wonder in equal measure. The May 2024 storm created auroras visible from all 50 US states, including Hawaii, bringing polar light shows to latitudes as low as 20 degrees from the equator. People in Phoenix and Miami and Mexico City looked up and saw colours that weren't supposed to be there. Reds and greens spreading across skies that had probably been auroral-free for a century or more, and the social response was remarkable. Millions of photographs shared online, people waking their neighbours, gatherings in parks and parking lots to witness something unprecedented in living memory, a collective experience of cosmic weirdness that briefly united people in shared wonder. These extreme expansions are previews of what could become more common if solar activity intensifies, reminders that the auroral zones are elastic boundaries that can stretch to encompass most of the planet during the right conditions. They're also warnings, because the same electromagnetic conditions that create beautiful displays at low latitudes also threaten infrastructure, inducing currents in power grids far from the poles, affecting satellites in orbits that normally experience minimal radiation, extending the reach of space weather into regions that rarely have to consider it. Auroras occur simultaneously in conjugate regions, mirror image locations in opposite hemispheres connected by the same magnetic field line. When particles precipitate into the atmosphere above Norway, creating a green curtain over Tromsø, their conjugate particles are simultaneously creating a nearly identical display in Antarctica, thousands of miles away, following the same magnetic field line down into the opposite hemisphere. This conjugate behaviour is one of the more elegant aspects of auroral physics, early evidence that the phenomenon is fundamentally symmetric, that Earth's magnetic field connects the poles not just conceptually, but literally, creating paths that particles follow from one hemisphere to another. The auroras are mirror twins, performing synchronized dances separated by half a planet's diameter, responding to the same magnetospheric conditions, connected through space by invisible magnetic geometry. Very few people have ever seen both members of a conjugate pair. It would require being in the Arctic and then somehow getting to Antarctica fast enough to see the same event, or having collaborators in both hemispheres photographing simultaneously. But satellite observations confirm the symmetry, show the same patterns appearing in both hemispheres at the same time, proof that the magnetic field line is a real connection, not just a theoretical construct. There's something profound about this linkage, about the idea that two regions separated by such vast distances are nonetheless connected, participating in the same electromagnetic event, experiencing the same solar wind influence expressed through the medium of Earth's magnetic field. It suggests that local is a complicated concept when magnetism is involved, that events occurring here are simultaneously occurring there. If the magnetic topology connects them, that space is knit together by invisible threads that make distance less relevant than geometry. Scientists discovered theta auroras in 2005, displays shaped like the Greek letter theta, with a circular or oval ring bisected by a line extending across the polar cap. These are rare formations that occur during specific solar wind conditions, typically when the interplanetary magnetic field points northward instead of its usual southward orientation, creating unusual magnetic topology in Earth's magnetosphere. Theta auroras last only hours, appearing and dissolving as solar wind conditions shift, geometric patterns drawn by electromagnetic forces following rules we're still working to fully understand. The circle represents the main auroral oval. The line crossing it marks a transpolar arc where particles are precipitating along field lines that have different connectivity than usual, creating a visual representation of magnetospheric reconfiguration. It's like the magnetic field is temporarily reorganizing itself, and the aurora is showing you the new structure, drawing a diagram in light that reveals invisible changes in field topology. These displays are scientifically valuable because they mark unusual magnetospheric states, conditions that don't occur often enough to be well characterized, opportunities to study Earth's magnetic field under stress or in configurations that aren't standard. But they're also just strange, visually peculiar in ways that make them stand out even among auroral phenomena. Most auroras follow familiar patterns: ovals, arcs, curtains, structures that repeat often enough to become recognizable. Theta auroras are outliers, shapes that appear wrong until you understand the unusual magnetic geometry that creates them. Reminders that the magnetosphere can adopt configurations outside the typical repertoire, that Earth's interaction with the solar wind has more modes than we usually see, most of them remaining latent until specific conditions trigger their expression. Auroral arcs can extend for thousands of miles, sometimes stretching from horizon to horizon like luminous highways in the sky, visible simultaneously from multiple countries, crossing time zones and political boundaries with complete indifference to human geography. A single arc might extend from Norway to Greenland, from Alaska across Canada to Hudson Bay, a continuous structure held together by magnetic field topology, particles precipitating along an extended region of favourable conditions. From any single viewing location, you see only a portion of the arc, the segment that happens to be above your horizon, but the full structure is enormous, continental in scale, an electromagnetic feature that rivals mountain ranges and ocean currents in its physical extent. And people separated by hundreds or thousands of miles can look up and see the same structure, the same arc, different portions of it, but recognizably the same phenomenon, a shared experience mediated by Earth's magnetic field. There's something unifying about this, about knowing that the green arc you're watching in Iceland is the same arc someone in northern Scotland is seeing, that you're both participating in the same event even though you're separated by ocean and distance, connected by your simultaneous observation of a single electromagnetic structure. The aurora becomes a kind of common reference, a shared context that crosses borders and cultures, evidence that we're all standing on the same planet beneath the same magnetosphere, in all equally subject to the same solar influences, all watching the same cosmic processes play out overhead. And the arc doesn't care about any of this, doesn't distinguish between Norwegian and Canadian sky, doesn't acknowledge boundaries or jurisdictions, just exists where the physics dictates, following field lines that care nothing for human organization of space, reminding us that natural phenomena operate on scales, and according to rules that make our subdivisions of the world seem arbitrary and small. The lower border of an auroral curtain is usually sharply defined, while the upper edge fades gradually into darkness. This asymmetry reveals something about atmospheric structure and the way particle precipitation works. The sharp bottom edge occurs because atmospheric density increases rapidly as you descend. Once particles reach an altitude where the air is thick enough, they suddenly start colliding with molecules frequently, and visible light production begins essentially all at once along a horizontal boundary. Above that boundary in thinner air, collisions are less frequent. Particles penetrate farther before interacting, and the light production is more spread out vertically, creating a gradual fade rather than a sharp cut-off. So the curtain shape is essentially a map of atmospheric density, a visible representation of how air thins with altitude, the sharp bottom marking where the threshold density for visible light production is reached, the fuzzy top showing the gradual transition into the near vacuum of higher altitudes. While you're seeing atmospheric structure made visible through particle physics, Earth's density profile rendered in light, and this structure is consistent across all auroral curtains. The bottom is always sharp, the top always diffuse, a pattern so reliable that you can use it to orient yourself, to understand what you're looking at, to read information about altitude and atmospheric conditions from the shape of the light alone. The aurora becomes instructional, teaching atmospheric physics to anyone who knows how to interpret it, offering lessons written in the geometry of illumination, in the distinction between sharp and diffuse boundaries, in the way light appears and disappears as particle precipitation encounters varying atmospheric densities. Not that you need to understand any of this to appreciate the beauty. The curtain is lovely regardless of whether you know why it has sharp and fuzzy edges, but the understanding adds another layer, transforms passive appreciation into active reading, lets you see physics as well as beauty in the dancing light. Auroral rays, vertical columns of light that extend upward from the main auroral structures, align with Earth's magnetic field lines, essentially showing you invisible magnetic geometry made temporarily visible. Each ray marks a field line along which particles are precipitating with particular intensity, creating a brighter column of light that stands out from the surrounding glow, pointing like an arrow toward the magnetic zenith, toward the direction that a magnetic field line above your location would follow into space. If you're standing directly beneath the auroral oval, if you're at the right latitude and the aurora is particularly strong, you might see a corona, rays appearing to converge at a point directly overhead, like looking up through a tunnel, or standing beneath a dome with pillars extending upward to meet at a central apex. This is entirely a perspective effect, like railroad tracks appearing to converge at the horizon. The rays are actually parallel, all following field lines that curve upward and eventually connect to the opposite hemisphere. But from your position on the ground, perspective makes them appear to meet above you. It's a stunning effect when you see it. This sense of standing beneath a cosmic cathedral with pillars of light rising all around you, meeting at a zenith that seems simultaneously infinite and intimate, lie close enough to feel overhead yet extending into depths you can't comprehend. The corona transforms the aurora from something you watch at a distance into something that surrounds you, that places you inside the geometry rather than outside it, that makes you feel embedded in the magnetic field rather than merely observing its visible manifestation. And in that moment, the aurora stops being a spectacle and becomes an environment, a three-dimensional electromagnetic structure within which you exist, a reminder that you're always inside Earth's magnetic field, always surrounded by these invisible lines of force, usually unaware of them but occasionally beautifully granted visual access to the architecture of magnetism that permeates your location. Some auroras produce distinct curtains that wave and ripple like fabric in a breeze, and though there's no wind in the thin air where they occur, the motion isn't mechanical, it's electromagnetic, waves propagating through plasma, fluctuations in the particle precipitation pattern that create the illusion of physical fabric moving when really it's just different molecules lighting up in sequence, patterns of excitation flowing through stationary gas. These ripples are plasma waves, oscillations in the electromagnetic field that affect particle trajectories, causing precipitation to intensify and weaken rhythmically across space. creating visual patterns that look like billowing curtains or flags waving in some cosmic wind. But the comparison to fabric is misleading. There's nothing solid there, no material that's actually waving. It's pure pattern, information propagating through a medium, like watching waves cross the ocean's surface while knowing that the water itself is just moving up and down, not travelling horizontally with the wave. The curtain doesn't move, the excitation pattern does, creating apparent motion through sequential illumination, tricking our pattern recognition systems into seeing fabric where there's only light. And yet the illusion is so compelling that it's hard not to perceive movement, hard not to feel like you're watching something physical wave and flow, hard to remember that you're seeing electromagnetic mathematics expressed as visual dynamics, physics pretending to be fabric so convincingly that our brains can't help but fall for it. Maybe that's one of the aurora's gifts. It makes electromagnetic field theory visible and tangible, translates invisible forces into visual metaphors we can grasp, thus teaches plasma physics through the language of curtains and waves and motion, making the abstract concrete even if the concreteness is technically illusory. The fastest auroral movements are called substorms, events where sudden releases of magnetic energy cause the lights to explosively expand and brighten, escalating from a quiet arc to a full sky display in minutes. These aren't gradual transitions. They're rapid, almost violent in their intensity, the electromagnetic equivalent of a dam breaking, stored energy in the magnetotail suddenly releasing and flooding into the polar regions. During a substorm, a calm auroral arc might suddenly brighten and begin moving rapidly poleward, thickening as it goes, spawning new structures, fragmenting into multiple curtains that dance and merge, filling the sky with light in a process that feels organic, almost alive in its urgency. The build-up is slower, energy accumulating in the magnetosphere over hours as the solar wind continuously transfers momentum and magnetic flux into Earth's magnetic field, storing it in the stretched field lines of the magnetotail like potential energy in a drawn bow. Eventually the system can't hold anymore, some threshold is crossed, and the stored energy releases in a cascade, snapping the bow, sending particles flooding earthward, creating the visible explosion of auroral activity. The whole cycle from build-up through release to recovery typically takes 2 to 3 hours, a rhythm that auroral scientists have studied extensively but still don't fully understand in all its details. Why does the release happen when it does? What exactly triggers the onset? How does the cascade propagate through the magnetosphere? These questions remain partially open, areas where observation and theory don't quite align perfectly, where we understand the general process but miss some crucial details. And so substorms continue, following their own logic, releasing energy on their own schedule, occasionally granting observers the gift of explosive expansion, the experience of watching the sky transform from quiet to ecstatic in real time, participating as witnesses to electromagnetic drama playing out overhead. Auroral coronas appear when you're standing directly beneath converging auroral rays, creating a crown-like effect overhead with pillars of light seeming to meet at a point above you. It's entirely a perspective phenomenon. You haven't moved to a different location within the aurora. The aurora has simply intensified or shifted such that you're now positioned beneath the convergence point of the rays, beneath the magnetic zenith where all the field lines passing through your location appear to meet. The effect is disorienting in the best way, transforming your relationship with the lights from horizontal observation to vertical immersion. Instead of looking at curtains in the distance, you're looking up through a tunnel of light, surrounded by rays on all sides, enclosed in luminous architecture that seems designed specifically for your location, as if the cosmos arranged itself around you. Of course, it's not personal. The rays are following magnetic field lines that have no awareness of your presence, but it feels personal. Feels like the aurora has noticed you, has created this formation specifically for your benefit. The corona is often the climax of a strong auroral display, the moment when diffuse glows and distant arcs intensify and reorganize into overhead structures, when the light goes from something you watch to something you're inside. And if you're fortunate enough to experience it, if you happen to be in the right place when a substorm creates overhead aurora, the effect is overwhelming in ways that photographs can't capture, that description struggles to convey. It's not just visual, it's spatial, emotional, almost spiritual in its impact. A moment when the boundary between observer and phenomenon collapses, when you stop watching the aurora and start participating in it, when the light stops being external and becomes environmental, surrounding, present in a way that demands acknowledgement not just with your eyes but with your entire being. The total power of auroral energy input into Earth's atmosphere during a moderate storm equals the entire electrical generating capacity of the United States, roughly 1 terawatt, 1 million megawatts, sustained for hours. Yet this immense energy arrives so spread out and so high up that it manifests as beauty rather than destruction, as light painting the sky rather than force damaging the surface. Think about that distribution for a moment. 1 terawatt is enough to power every city, every home, every device in a nation of 330 million people. It's staggering energy. The output of 1,000 large power plants running simultaneously. But instead of arriving at power outlets and charging stations and light fixtures, it arrives in the upper atmosphere, spread across millions of square miles, deposited as heat and light in air so thin that the total thermal effect is negligible. The atmosphere absorbs this energy without significant temperature change, converts it to photons that stream down to the ground where we see them as auroras, and the whole process happens so gently, so diffusely, that the primary effect is aesthetic rather than thermal or mechanical. It's like the difference between a spotlight and sunlight on a summer day. Both might deliver the same total energy to your yard, but the spotlight would be blinding and possibly dangerous while the sunlight is pleasant and warming because it's spread out. Auroras are the ultimate distributed energy system, cosmic power delivered so kindly that we can stand beneath it safely, admiring the display without being harmed by the energies creating it. And there's something reassuring about this, about living in a universe where terawatt-scale energy transfers can be beautiful, where electromagnetic violence can be rendered harmless through geometry and distribution, where we can witness processes that dwarf human scale without being destroyed by them. Auroras affect the chemistry of Earth's upper atmosphere, creating nitrogen oxides that eventually drift down through the atmospheric layers and settle into polar soils, adding nutrients that contribute to plant growth in an unexpected cycle, connecting space weather to terrestrial biology. The energetic particles that create the lights also break apart nitrogen and oxygen molecules, allowing them to recombine in new configurations, creating compounds that wouldn't form under normal atmospheric conditions. These nitrogen oxides are created at altitudes of 60 to 200 miles, far above where plants grow, but atmospheric circulation eventually brings them down, mixing them through lower layers, depositing them as nitrates in rainfall and snowfall, fertilizing Arctic and Antarctic vegetation with nutrients that originated in electromagnetic interactions between solar wind and upper atmosphere. It's a cosmic nitrogen cycle, space weather contributing to soil chemistry, auroras indirectly feeding plants through a process that takes months or years to complete, but that has probably been operating for billions of years since Earth first developed a magnetic field and atmosphere. And this means that the auroral zones are not just electromagnetically active but biogeochemically enriched, receiving nutrient inputs from space-mediated chemistry, benefiting from processes that connect the magnetosphere to the biosphere in ways that are subtle but measurable. Plants growing in polar regions are partly fed by auroras, by nitrogen fixed through electromagnetic interactions rather than biological or industrial processes, by atoms that were excited by solar particles and then slowly, gradually, made their way down through the atmosphere to become part of the soil, the vegetation, the food web. It's another reminder that Earth systems are interconnected, that space weather and soil chemistry and plant biology are not separate domains but parts of a larger integrated system, that the auroras overhead are not isolated from the life below, but participant in cycles that span from magnetosphere to biosphere, from space physics to ecology. During solar minimum, the quiet part of the Sun's 11-year cycle, auroras still occur but tend to be fainter and confined to higher latitudes, appearing only in the deepest polar regions where the auroral oval maintains its baseline position. These minimum phase auroras are subtle, often just faint green glows on the northern horizon, barely enough to notice unless you're specifically watching for them, easy to miss if you're not patient or don't have dark adapted eyes. But even in this quiet state, the fundamental process continues. The solar wind never completely stops, never falls to zero, even during the sun's calmest periods. There's always some stream of particles flowing outward, always some interaction with Earth's magnetic field, always some precipitation into the polar atmospheres. The auroras become whispers instead of shouts, suggestions instead of declarations, but they persist, maintaining their presence even when conditions are unfavourable for spectacular displays. And there's something oddly comforting about this continuity, about knowing that the process doesn't shut off, that there's always some auroral activity happening somewhere in the auroral zones, that the electromagnetic dialogue between Sun and Earth continues even when it's too quiet for most people to notice. These solar minimum auroras are for dedicated watchers, for people willing to drive to remote locations and wait in cold darkness for faint glows that might appear for only minutes, for those who find beauty in subtlety rather than spectacle. They're proof that not all valuable experiences are dramatic, that sometimes the reward is in noticing what's barely there, in appreciating the quiet persistence of natural processes that continue regardless of whether they're currently impressive. The Sun's magnetic field flips polarity every 11 years at solar maximum, part of a larger 22-year cycle that influences long-term auroral patterns in ways we're still working to fully understand. The 11-year sunspot cycle is actually only half of a complete magnetic cycle. The Sun's north and south magnetic poles swap positions, then swap back again, creating a full cycle that takes roughly 2 decades to complete. This polarity reversal affects how the solar wind interacts with Earth's magnetic field, changing the probability distributions for various types of auroral activity, subtly modulating the long-term statistics of geomagnetic storms and auroral displays. Some solar cycles produce more intense storms than others, variations that might be related to the polarity state, to how the Sun's magnetic field is oriented relative to Earth's during different parts of the 22-year cycle. But the correlations are weak, the patterns are noisy, and we don't yet have enough observational data, a few centuries at most, covering only a dozen or so complete cycles, to say with certainty how the 22-year cycle affects auroral climatology. We're still learning the Sun's rhythms, and still trying to understand how its magnetic field evolves and what that evolution means for Earth. The Sun has been following these cycles for billions of years, breathing in and out magnetically, flipping its poles regularly, creating patterns that persist across timescales far longer than human civilization. We're catching glimpses of the pattern, measuring what we can, building models that capture some aspects while missing others, participants in a cosmic dance whose full choreography remains partially hidden, whose rules we're inferring from limited observations of an ongoing process that began before Earth existed and will continue long after we're gone. Coronal mass ejections, massive eruptions of plasma from the Sun, create the most spectacular auroral displays when they strike Earth. These are billion-ton waves of magnetized plasma, entire regions of the Sun's corona torn loose and flung into space, carrying their own twisted magnetic fields, travelling at speeds that can exceed the normal solar wind by factors of 3 or 4. When a CME hits Earth, the impact compresses our magnetosphere, sometimes pushing it back to half its normal distance, overwhelming the usual protective mechanisms, forcing open channels for massive particle precipitation. The resulting auroras can be visible from tropical latitudes, can last for days as the Earth-directed portion of the CME streams past, can create displays so bright and so extensive that they enter historical records, that shape legends and myths, that mark particular nights as exceptional in human memory. The Carrington event was a CME impact. The Quebec blackout was a CME impact. The great auroral displays that create once-in-a-lifetime experiences are almost always CME-driven. Events where the Sun doesn't just send particles, but throws entire chunks of itself toward Earth, magnetic structures that slam into our magnetosphere and temporarily reorganize it, creating conditions far outside the normal range. And CMEs are somewhat predictable now. We can see them leave the Sun, can track them across the Sun-Earth gap, can estimate their arrival time and likely impact, but they remain essentially chaotic, each one slightly different, each impact creating unique responses in Earth's magnetosphere, each auroral display shaped by the particular magnetic topology of that specific CME. They're cosmic individuals, these plasma clouds, not identical copies but variations on a theme, each carrying its own magnetic personality that expresses itself through the auroras it creates when it collides with our magnetic field. Scientists use radar to study auroras, bouncing radio waves off the ionized trails left by auroral particles, detecting structures and dynamics invisible to optical observation. These radar systems can see auroras through clouds, through daylight, through any visual obstruction, because they're not detecting light, but rather the ionization, the changes in atmospheric conductivity caused by particle precipitation. This allows continuous monitoring regardless of weather or solar angle, creates datasets that span years without gaps, reveals aspects of auroral structure that light-based observations miss. The radar sees electrons, sees how charge density varies with altitude and time, sees waves and instabilities in the ionosphere that are auroral markers even when they're not producing visible light. It's like having X-ray vision for the aurora, seeing through the surface phenomenon to the underlying electromagnetic structure, detecting causes rather than just effects. And the radar data often reveals that visual auroras are just part of the story, that there's auroral activity, particle precipitation, ionospheric modification, current systems, happening continuously, most of it invisible, only occasionally intense enough to produce light we can see. The aurora we photograph represents peak activity, moments when the precipitation is strong enough and at the right altitude to create visible emissions, but beneath and around those visible events are constant lower-level processes and ongoing electromagnetic interactions that radar can detect but our eyes cannot. It's another reminder that human perception captures only a narrow slice of reality, that what we see is a subset of what's happening, that the universe operates in multiple domains simultaneously, and we're only directly aware of the few that happen to overlap with our sensory capabilities. The aurora is larger than its visible manifestation, extends into radar frequencies and X-ray emissions, and ionospheric conductivity changes, exists across multiple measurement domains simultaneously, a multifaceted phenomenon of which light is just the most accessible component. Auroras produce electromagnetic waves called auroral kilometric radiation that can be picked up by radio receivers, creating bursts of static and noise that sound like cosmic rain, like the sky hissing and crackling in frequencies far below human hearing but detectable as radio signals. These emissions occur at frequencies between 50 and 500 kHz in the AM radio band, generated by the same particle acceleration processes that create visible light, but radiating outward as electromagnetic waves instead of photons. You can't hear them directly, they're outside the acoustic range, but if you have a radio receiver tuned to the right frequencies, you can detect them, can listen to the aurora speaking in radio wavelengths, adding an auditory dimension to what's primarily a visual phenomenon. The character of the radio emissions changes with auroral intensity, becoming louder and more chaotic during substorms, quieting during quiescent periods, creating a kind of soundtrack that matches the visual display if you're watching and listening simultaneously. It's nature's own radio station, broadcasting from the auroral zones, sending signals that propagate through Earth's magnetosphere and into space, detectable by satellites, by ground stations, by anyone with appropriate receivers. And the fact that auroras make radio emissions adds another layer to their complexity, another domain in which they express themselves, another way in which the same fundamental process, particle precipitation and electromagnetic interaction, creates multiple different outputs depending on what you're measuring. The aurora is a multimedia event, performing simultaneously in visible light, radio waves, X-rays, each wavelength revealing different aspects of the underlying physics, like each measurement technique capturing a different facet of the same phenomenon, collectively creating a fuller picture than any single observation method could provide alone. All sky cameras positioned around the Arctic and Antarctic create time-lapse networks that track auroras across entire continents, automated sentinels that watch every night regardless of weather or human presence, building archives of auroral activity that span years and capture displays that would otherwise exist only in the moment, seen by no one or by scattered individuals gone without record. These cameras have revolutionized auroral science, replacing sporadic human observations with continuous monitoring, allowing researchers to study auroral dynamics at continental scales, to track how structures propagate across thousands of miles, and to analyze statistical patterns that only emerge from large datasets. And they've democratized aurora watching in a sense, making it possible for people anywhere to see what's happening over the poles in real time, to check camera feeds from Tromsø or Fairbanks or McMurdo, to participate virtually in auroral observations even from locations that never see the lights directly. The cameras don't sleep, don't get cold, don't lose interest during quiet periods. They just watch, night after night, accumulating images, creating time-lapse sequences that compress hours into seconds, revealing motion patterns invisible to observers watching in real time, and in the process, they've captured phenomena that would have been missed entirely. Rare formations, brief intensifications, structures that appeared over unpopulated regions where no human was watching, events that existed for minutes and then disappeared, preserved now in digital archives, available for analysis by researchers who can study them at leisure, can compare them to other events, can build understanding from observations that would otherwise be lost to time. Auroral electrons can gain energy from their interactions with Earth's magnetic field, sometimes emerging with more energy than they had going in. A process that violates no laws of physics because they're borrowing energy from the rotating magnetic field itself, converting electromagnetic field energy into particle kinetic energy through wave-particle interactions that act as cosmic accelerators. This energy gain happens through resonant interactions between electrons and naturally occurring electromagnetic waves in the magnetosphere. Whistler mode, chorus waves for example, can energize electrons to higher velocities, kicking them to radiation belt energies, creating populations of very energetic particles that can penetrate deeper into the atmosphere or remain trapped in the radiation belts for extended periods. It's a complex dance between waves and particles, each affecting the other, creating feedback loops where wave growth depends on particle distributions and particle energies depend on wave interactions. The result is a dynamic system that can accelerate particles to energies far exceeding what the solar wind delivers directly, creating energetic populations through in situ processes, turning Earth's magnetosphere into a particle accelerator on a planetary scale. And these accelerated particles contribute to auroral displays, to radiation belt hazards, to space weather effects that extend beyond simple particle precipitation, creating a richer, more complex electromagnetic environment than you'd have from solar wind alone. The magnetosphere is not passive, not just a shield that deflects particles. It's active, energetic, capable of taking incoming particle populations and modifying them, accelerating some, decelerating others, creating new distributions that then precipitate into the atmosphere and create auroras whose origins are partly terrestrial rather than purely solar. Earth contributes to its own auroras, adds its own energy to the system, or participates as an active agent rather than just a recipient of solar influence. The boundary between open and closed magnetic field lines in Earth's magnetosphere, where auroras preferentially form, shifts constantly, a dynamic frontier in perpetual flux, responding to solar wind variations, to magnetospheric instabilities, to processes occurring thousands of miles overhead that translate within minutes to changes in auroral position and intensity on the ground. Open field lines are connected to the solar wind, one end attached to Earth and the other extending into interplanetary space, allowing particles to stream along them from the solar wind directly into the polar atmosphere. Closed field lines are loops, both ends attached to Earth, trapping particles in the inner magnetosphere, keeping them isolated from direct solar wind access. The boundary between these regions, called the open-closed field line boundary, is where the most intense auroras typically occur, where particles have access to both magnetospheric energy and direct solar wind input, where conditions are optimal for bright structured displays. But this boundary isn't fixed. It moves, oscillating poleward and equatorward, responding to changes in solar wind pressure and magnetic field orientation, to magnetospheric reconfigurations during substorms, to processes that open previously closed field lines or close previously open ones. The aurora tracks this moving boundary, appearing where the geometry is favourable, disappearing when field lines close or open in ways that reduce particle access. So when you watch an aurora move across the sky, you're watching the manifestation of magnetic topology changes happening in space, seeing the shadow of invisible reconfigurations projected onto the atmosphere as moving light, observing geometry through its luminous consequences rather than directly. Artificial auroras have been created by high-altitude rocket experiments, releasing chemicals like barium into the upper atmosphere, creating temporary glowing clouds that allow scientists to trace magnetic field lines and atmospheric currents with visible markers. These human-made light shows serve a different purpose than natural auroras. They're diagnostic tools, experiments designed to reveal invisible structures, to map what can't normally be seen. When barium vapor is released at high altitude, it ionizes in sunlight, creating clouds of charged particles that glow and that respond to magnetic fields, drifting along field lines, tracing out the geometry in three-dimensional space. Observers on the ground see expanding clouds of luminescent gas, sometimes green or blue-green, sometimes structured into rays or spreading formations that reveal how the magnetic field is oriented at that location and altitude. These artificial auroras last only minutes, dispersing as the barium cloud expands and dims, but during their brief existence they make the invisible visible, turn abstract field line diagrams into concrete visual phenomena. And they help scientists understand natural auroras by providing controlled conditions, known inputs, situations where you can predict what should happen and then observe whether reality matches prediction. The artificial auroras are too faint and too brief to rival natural displays. They're scientific instruments, not entertainment, but they represent humanity's growing ability to probe and manipulate the environment at auroral altitudes, to conduct experiments in the ionosphere, to test our understanding through active intervention rather than just passive observation. We're moving from merely watching auroras to creating simplified versions of them, from observation to experimentation, from wondering what creates the lights to demonstrating the principles in controlled releases, taking the mystery and making it, piece by piece, into understood physics that we can reproduce on demand. The HAARP facility in Alaska can induce very faint artificial auroras by energizing the ionosphere with powerful radio waves, heating small regions of the upper atmosphere until they glow faintly, creating human-made light shows that are far fainter than natural auroras, but that demonstrate our growing ability to manipulate the electromagnetic environment. HAARP stands for High Frequency Active Auroral Research Program, and it consists of an array of radio transmitters that can pump megawatts of power into the ionosphere, temporarily modifying its properties, creating plasma instabilities, generating extremely low-frequency waves. The artificial auroras it creates are barely visible, requiring sensitive cameras to detect, nothing like the brilliant natural displays that occur during geomagnetic storms. But they're proof of concept, demonstrations that we can affect the ionosphere deliberately. Yeah, that we understand enough about auroral physics to create simplified versions through technological means. The implications are complex. On one hand, it's basic research, experiments designed to understand how the ionosphere responds to energy input, how plasma instabilities develop, how we might mitigate space weather effects or improve radio communications. On the other hand, it represents an expansion of human influence into domains we've historically only observed, capabilities that raise questions about appropriate use and unintended consequences. HAARP attracts conspiracy theories partly because it's genuinely doing something unusual, modifying the ionosphere, creating artificial auroras, experimenting with electromagnetic manipulation at scales that feel cosmic, even if the actual effects are small. And the reality is less dramatic than the theories suggest, but more interesting in its own way. We're learning to touch the aurora, to create pale imitations of natural phenomena, to experiment with processes that have occurred naturally for billions of years, bringing them under partial human control, transforming passive observation into active experimentation, becoming participants in electromagnetic processes we once could only witness. Jupiter's auroras are powered partly by volcanic eruptions on its moon Io, which spews sulfur and oxygen into Jupiter's magnetosphere at rates that dwarf any volcanic activity on Earth. Io is the most volcanically active body in the solar system, constantly erupting, constantly injecting material into the space around Jupiter, and that material becomes ionized. Io gets caught in Jupiter's powerful magnetic field and contributes to auroral processes that are orders of magnitude more energetic than Earth's. In essence, a moon's volcanism creates another planet's light show, an interplanetary connection that spans hundreds of thousands of miles, linking geologic activity on a small moon to electromagnetic phenomena on a gas giant. The particles from Io form a torus, a donut-shaped cloud of plasma orbiting Jupiter at Io's distance, and material from this torus gets swept up by Jupiter's magnetic field, accelerated to high energies, and slammed into Jupiter's upper atmosphere at both poles, creating permanent auroral ovals that glow continuously in ultraviolet wavelengths. Unlike Earth, where auroras are intermittent and dependent on solar wind variations, Jupiter has baseline auroral activity that never stops, powered by the combination of solar wind and volcanic outgassing, creating a hybrid system where both external and internal sources contribute to the displays. And this reminds us that auroral physics is universal, but the details vary wildly, that while the basic process, charged particles exciting atmospheric gases, works the same everywhere, the sources of those particles, the strength of the magnetic fields, the composition of the atmospheres all differ from world to world, creating unique expressions of the same fundamental phenomenon. Jupiter's auroras are alien, more powerful than Earth's by factors of hundreds, ultraviolet rather than primarily visible, permanent rather than intermittent, fed by volcanic moons rather than just solar wind. They're what auroras look like on a world with a magnetic field 10 times stronger than Earth's, with an atmosphere of hydrogen and helium, with satellites that are geologically hyperactive. They're familiar in principle, but exotic in detail, recognizable as auroras but utterly unlike what we see in our polar skies. Saturn's auroras appear to be influenced by its rings, with particles from ring material contributing to the plasma environment that feeds auroral processes. The rings are constantly eroding, shedding material that becomes ionized and contributes to Saturn's magnetosphere, adding complexity to auroral dynamics in ways that don't occur on ringless planets like Earth. The same rings that grace Saturn with visible splendor, those vast disks of ice and rock that make it the solar system's most photogenic planet, also feed invisible processes that paint Saturn's poles with ultraviolet light, connecting surface features to electromagnetic phenomena through mechanisms that are still being researched. The rings rain material onto Saturn, particles spiraling inward along magnetic field lines, contributing to atmospheric chemistry and auroral emissions at specific latitudes, and this creates asymmetries, variations in auroral intensity that correlate with ring structure, patterns that reveal how material is flowing from rings to planet through electromagnetic pathways. It's another example of how planetary systems are integrated, how what happens in one domain affects others, how you can't fully understand Saturn's auroras without also understanding its rings, and vice versa. The aurora becomes a diagnostic, a way to study ring erosion rates and particle transport, a visible, ultraviolet visible consequence of processes occurring in the rings themselves, and it suggests that auroral science on other worlds is necessarily multidisciplinary, requiring understanding of geology, atmospheric science, magnetospheric physics, and even astrophysics of dust and ice, all combined to explain why the lights appear where they do, when they do, with the intensities and structures observed. Each planet teaches us something different about auroral physics, adds new variables to the equations, demonstrates that while we understand the basics, the full richness of auroral phenomena requires accounting for local conditions, unique features, specific circumstances that make each world's auroras distinct. Brown dwarfs, failed stars too small to sustain fusion, can have auroras millions of times more powerful than Earth's, driven by their own rotation and magnetic fields rather than by any external wind. These objects exist in the gap between planets and stars, too massive to be planets, but not massive enough to fuse hydrogen, radiating away their formation heat over billions of years, glowing dimly in infrared wavelengths. But some brown dwarfs also glow in radio wavelengths, producing emissions consistent with auroral processes, with charged particles spiraling along magnetic field lines and radiating as they accelerate. These brown dwarf auroras aren't driven by stellar wind. There's no star for them to orbit, or they orbit stars too distant to provide significant particle input. Instead, they're powered by the brown dwarf's own rotation, by its magnetic field interacting with surrounding plasma, by internal dynamos that generate magnetic fields similar to Jupiter's, but often much stronger. The auroras are radio emissions rather than visible light, occurring in atmospheres of hydrogen and helium at temperatures where water would boil, on worlds that have no solid surface, just gradually thickening gas all the way down to the core. They're auroras in a regime completely different from Earth's, on objects that aren't quite planets and aren't quite stars, demonstrations that auroral physics applies across a vast range of conditions, and from rocky planets with thin atmospheres to massive failed stars with no solid surface at all. And they're likely common, occurring on brown dwarfs throughout the galaxy, invisible to optical telescopes but bright in radio, contributing to the electromagnetic background of the cosmos, auroras that no eye will ever see directly, that exist in wavelengths requiring radio telescopes to detect, on worlds that will never be visited, that are too dim to easily spot and too exotic to easily understand, but that nonetheless participate in the same fundamental electromagnetic processes that create the northern lights over Earth's poles. Exoplanets orbiting close to their stars might have permanent, ultra-intense auroras on the side facing their sun, tidally locked into endless electromagnetic bombardment. These hot Jupiters, as they're called, does orbit so close that stellar wind intensity far exceeds what Earth experiences, and if they have magnetic fields, they would interact with that wind continuously, creating auroral activity that never ceases, that has no day-night cycle, because the same hemisphere always faces the star. Imagine a world where half the planet is perpetually bathed in auroral light, where the stellar-facing hemisphere has continuous particle precipitation, creating constant glows in whatever wavelengths the atmosphere emits, where the electromagnetic environment is so intense that the aurora isn't an occasional phenomenon, but a permanent feature, as constant as sunlight. These are speculative scenarios. We can't directly observe auroras on exoplanets yet. Can't resolve the necessary details even with our best telescopes, but the physics suggests they should exist, that any magnetized planet close to an active star will experience continuous electromagnetic interaction, continuous auroral activity, modulated only by changes in stellar output, rather than by planetary rotation or orbital position. And these auroras would be extreme, powered by stellar winds potentially hundreds of times more intense than Earth's solar wind, creating displays that would dwarf anything seen in our solar system, making Jupiter's auroras look faint by comparison. They're auroras in a regime we can only imagine, on worlds we'll likely never visit, but they're probably out there scattered throughout the galaxy, billions of planets with permanent light shows that no one will ever witness directly. The beauty occurring in isolation, auroral processes playing out on worlds without observers, without anyone to appreciate them, electromagnetic interactions continuing regardless of whether consciousness exists anywhere nearby to notice or care. The universe creates auroras wherever the conditions permit, indifferent to observation, indifferent to appreciation, producing beauty as a side effect of physics, with or without an audience. The colours you see in aurora photographs often differ significantly from what your eyes perceive, because cameras can capture long exposures and different wavelengths, accumulating light over seconds or minutes that your eyes experience as fleeting moments, amplifying faint emissions into vivid displays. Many of the vivid reds and purples in photographs appear as pale greens or barely visible glows to the naked eye, or sometimes don't appear at all, existing below the threshold of human colour vision. Our eyes have two types of photoreceptors, rods for low-light vision and cones for colour. In darkness, our rods dominate, giving us sensitivity but sacrificing colour discrimination. We see auroras primarily with our rods, which means we see them mostly in shades of grey and green, with other colours either invisible or perceived as faint hints of hue rather than vivid saturation. Cameras don't have this limitation. They can accumulate light for 10, 20, 30 seconds, gathering photons that our eyes would never integrate, building up signal until faint red emissions become vivid crimson, until barely visible purples become prominent magenta. The camera's image is more complete in one sense. It captures wavelengths and intensities that are genuinely present, but it's also misleading, creating expectations that don't match direct visual experience. First-time aurora watchers often feel disappointed because reality doesn't match the photographs they've seen, because the colours are more subtle, the brightness more moderate, the overall effect more understated than the images suggested. But maybe this discrepancy is valuable. Maybe it preserves something important about the auroral experience, the need for patience, for dark adaptation, for allowing your eyes time to gather light and your perception time to adjust, the requirement that you be present and attentive rather than expecting immediate dramatic gratification. The camera captures what's there, but the eye experiences what matters, and they're not quite the same thing. Auroral forecasting has become sophisticated enough to predict not just whether auroras will occur, but approximately where the best viewing will be, with apps and websites offering real-time alerts based on solar wind data, magnetometer readings, and atmospheric conditions. These forecasts democratize knowledge that was once specialized, making space weather accessible to anyone with a smartphone, allowing casual observers to plan aurora watching trips with reasonable confidence that they'll see something. The forecast systems ingest data from satellites monitoring the solar wind, from ground-based magnetometer networks tracking geomagnetic activity, from all-sky cameras reporting current conditions, combining these inputs into predictions about auroral probability over the next hours or days. They're not perfect. The magnetosphere is chaotic. Small variations in initial conditions can produce large differences in outcomes, but they're good enough to be useful. Accurate enough that following the forecasts increases your odds substantially compared to just hoping you'll get lucky. And this represents a shift in how humans relate to auroras, from passive recipients of whatever happens to show up, to active planners who can optimize their chances, who can decide whether to drive to dark locations based on predicted probabilities, who can set alarms for predicted substorm times. We've brought auroras partially under informational control, not influencing whether they occur but knowing when they're likely, reducing uncertainty, making the experience more accessible to people who can't just wait indefinitely in Arctic darkness hoping for displays. Some might argue this diminishes the magic, that adding predictability reduces the sense of fortune and wonder when auroras appear. But it also enables experience, allows people who couldn't otherwise participate to plan and travel and witness, democratizes access to phenomena that were once available only to those with unlimited time and resources, or those lucky enough to live in the auroral zones. The auroral substorm cycle, from quiet arc to explosive expansion to recovery, typically lasts about 2 to 3 hours, a natural rhythm that repeats throughout geomagnetic storms, a breathing pattern of energy accumulation and release that organizes auroral activity into quasi-predictable intervals. Understanding this rhythm allows observers to anticipate when activity might intensify, when to be especially watchful, when the quiet arc on the northern horizon might suddenly brighten and spread across the entire sky. The cycle begins with the growth phase, when energy is loading into the magnetotail, storing magnetic stress that will eventually release. During this phase, the aurora might be a quiet arc, stable, unchanging, giving no obvious indication that anything dramatic is about to happen. But magnetometers detect the build-up, measure increasing asymmetry in the magnetic field, trace the signature of energy accumulation. Then comes the expansion phase, sudden onset, the stored energy releasing in a cascade that sends particles flooding into the polar atmosphere, creating the visible explosion of auroral activity. This is the spectacular part. The moment when quiet arcs transform into dancing curtains, when the sky fills with light and motion, when observers realize something significant is happening. And finally, the recovery phase, as the system relaxes back toward equilibrium, the aurora fading and retreating, returning to quiet arc or diffuse glow, resetting the cycle so it can begin again if solar wind conditions remain favourable. 3 hours from start to finish, more or less, with variations depending on solar wind driving and magnetospheric state, but consistent enough that if you watch a strong auroral display for several hours, you'll likely see this pattern repeat, see multiple cycles of intensification and relaxation, witness the magnetosphere's rhythmic response to continuous solar wind driving. It's a pulse, a heartbeat, electromagnetic respiration made visible through auroral light, sprites and elves, exotic electrical phenomena that occur above thunderstorms, share some physics with auroras despite forming at different altitudes and from different causes. Both involve electrical discharge in the upper atmosphere. Both create light through excitation of atmospheric gases. Both are examples of how Earth's atmosphere can light up from electrical processes, whether driven from below by thunderstorms or from above by particle precipitation. Sprites are reddish flashes that extend from the tops of thunderclouds up to 50 or 60 miles altitude, happening so quickly, lasting only milliseconds, that they were considered legendary until pilots started reporting them, and high-speed cameras finally captured them in the 1990s. Elves are expanding rings of light that ripple outward at the bottom of the ionosphere, electromagnetic pulses from lightning interacting with ionospheric electrons. Both phenomena occupy the same altitude range as lower auroras. Both involve similar excitation mechanisms. Both demonstrate that the mesosphere and lower ionosphere can produce visible emissions through electrical processes. And this suggests that Earth's upper atmosphere is more electrically active than we once thought, that there are multiple pathways to creating light at high altitudes, that auroras are just one category of upper atmospheric luminescence, sharing space with transient luminous events driven by tropospheric electricity. The sky between where weather happens and where space begins is populated with exotic phenomena, most of them too brief or too faint to see without specialized equipment, but all of them evidence that the atmosphere is electrically dynamic from surface to space, conducting and discharging and lighting up in response to various energy inputs. Auroras are the most sustained and predictable of these phenomena, but they're part of a larger family of atmospheric electrical displays, a spectrum of ways that our planet's air can glow when energized appropriately. The term space weather was coined in the 1990s to describe the conditions in near-Earth space that affect auroras and technology, extending meteorology into the cosmic realm, acknowledging that the space environment changes and fluctuates and has impacts just as terrestrial weather does. Before this conceptual shift, solar activity and geomagnetic disturbances were studied by specialized researchers in separate disciplines, but they weren't integrated into a unified framework of weather that the public could understand or that forecasters could predict using tools similar to atmospheric weather forecasting. Now we have space weather prediction centers that operate much like hurricane forecast centers, monitoring solar activity, issuing alerts when coronal mass ejections are Earth-directed, warning satellite operators and power grid managers about incoming geomagnetic storms, providing the same kind of advance notice and risk assessment that meteorologists provide for terrestrial storms. And this reframing matters because it acknowledges that space isn't empty, isn't static, isn't a void separate from the dynamic systems we're familiar with on Earth's surface. Space has weather, has conditions that vary from calm to stormy, has phenomena that can be forecast with reasonable accuracy given sufficient monitoring and modelling. Auroras are one aspect of space weather, the beautiful visible manifestation, but the same conditions that create auroras also affect satellites, radiation exposure for astronauts, radio communications, power grids, GPS accuracy, a whole suite of impacts that matter for modern technological civilization. We've extended weather forecasting beyond the troposphere, beyond the domain where clouds form and winds blow, into the magnetosphere and solar wind, tracking storms measured in plasma density and magnetic field orientation, rather than pressure systems and temperature gradients. And in doing so, we've acknowledged something important: that Earth exists in a dynamic environment, that the space around us is not empty, but filled with variable conditions, that we need to monitor and predict those conditions with the same seriousness we bring to hurricane tracking or tornado warnings. Auroras contribute to the depletion of Earth's upper atmosphere, with particles escaping to space during intense events as the energy deposited by auroral precipitation heats the thermosphere, increasing its temperature and causing it to expand upward, lifting molecules to altitudes where they can escape Earth's gravity. This atmospheric loss is happening constantly, but accelerates during major geomagnetic storms, when auroral energy input heats the upper atmosphere substantially, causing atmospheric expansion that allows lighter molecules, hydrogen and helium primarily, to reach escape velocity and drift away into space. The rate of loss is small, negligible on human timescales, but over geological time it adds up. Earth has lost a significant fraction of its original atmosphere to space over billions of years, and auroras are one mechanism contributing to that loss, though not the dominant one. The planet replenishes atmospheric losses through volcanic outgassing, through cometary impacts, through various processes that bring volatiles from the interior to the surface, maintaining a rough balance that has sustained our atmosphere despite continuous losses to space. But the balance isn't perfect, and over very long timescales, billions of years, Earth's atmosphere will continue evolving, thinning gradually unless replenishment mechanisms remain active. Every major aurora steals a tiny piece of Earth's air, accelerates molecules to escape velocity, sends them on one-way journeys into interplanetary space where they become part of the solar wind, atoms that once were part of our atmosphere now scattered throughout the inner solar system. It's a slow bleeding, imperceptible on human timescales but real, measurable, evidence that planets aren't static but evolving, that atmospheres are temporary features on geological timescales, maintained only as long as sources balance losses. The aurora is simultaneously life-sustaining, creating nutrients, protecting from radiation, and slowly destructive, gradually eroding the air we breathe, contributing over deep time to changes that will eventually leave Earth's atmosphere thinner, less protective, less capable of sustaining life as we know it. But that's billions of years away, time enough for continents to rearrange multiple times, for the Sun to evolve through substantial portions of its main sequence lifetime, for anything resembling current life to become unrecognizable. Ancient Japanese records describe auroras as red clouds or fans spreading across the northern sky. Observations from latitudes where auroras are rare, suggesting periods of higher solar activity centuries or millennia ago. These historical documents, court records, astronomical logs, literary descriptions, preserve observations from times before systematic scientific monitoring, before we had magnetometers or satellites or any modern instrumentation, just human eyes and the discipline to record what they saw. The fact that Japanese observers saw auroras, sometimes repeatedly over decades, suggests that solar activity during certain historical periods was elevated compared to modern baselines, that the auroral oval expanded southward more frequently, that geomagnetic storms intense enough to bring auroras to mid-latitudes occurred with higher frequency than they do today. These records allow researchers to reconstruct solar activity over centuries, to identify periods of high and low activity before we had telescopes to observe sunspots or instruments to measure geomagnetic fields, to extend our understanding of solar variability back beyond the instrumental era. And they remind us that the aurora has been human observable for as long as humans have existed, that people have always looked up and seen these lights when conditions permitted, either that we're part of a long chain of observers stretching back through recorded history and presumably much farther into prehistory, all experiencing the same phenomenon we see today, all trying to make sense of it within their cultural frameworks, all leaving records, some written, some oral, some artistic, that preserve their encounters with the unexplained lights in the sky. The aurora connects us to our ancestors, provides a shared experience across millennia, demonstrates that some phenomena are so striking they compel documentation regardless of whether the documenter understands what they're seeing. The ancient Japanese astronomers didn't know about plasma or magnetic fields, but they knew something significant was happening, knew it was worth recording, and their records now help us understand solar cycles that occurred before anyone could measure them directly. The thickness of an auroral curtain can be less than a mile, even though it extends thousands of miles horizontally, making these structures incredibly thin relative to their other dimensions, like cosmic sheets or banners hung across the polar sky. If you scaled an auroral curtain down to something you could hold, it would be thinner than tissue paper, more like a soap bubble, a surface with almost no depth but significant extent. This thinness results from the physics of particle precipitation. Particles follow magnetic field lines down into the atmosphere, and those field lines are organized into sheets or curtains by magnetospheric processes, creating regions where precipitation is concentrated into narrow vertical ranges. The curtain appears where particles are hitting the atmosphere at a specific altitude range, and because atmospheric density increases rapidly with decreasing altitude, there's only a narrow vertical band where conditions are optimal for visible light production. Above that band, the air is too thin for frequent collisions. Below it, particles have already deposited their energy and stopped producing light. The result is a thin layer of illumination, stretched horizontally across vast distances, but compressed vertically into remarkably narrow structures. And this thinness has observational consequences. If you could somehow fly through an auroral curtain, and astronauts on the ISS occasionally do, you'd be inside it for only seconds despite travelling at orbital velocity. Now passing through this luminous sheet so quickly that it would seem more like a boundary than a volume. The curtain is surface-like, two-dimensional, stretched through three-dimensional space. Evidence that auroral structures follow magnetic topology more than atmospheric structure, that they're organized by fields rather than by altitude or pressure or any purely atmospheric parameter. They're magnetic phenomena that happen to be visible, geometry imposed from space onto the atmosphere, patterns that reveal invisible structures through their luminous manifestations. auroras can induce electrical currents in the ocean, measurable as electromagnetic fluctuations in seawater that scientists can detect with underwater sensors. The rapidly changing magnetic fields associated with auroral currents in the ionosphere induce secondary currents in any conductor, and seawater, with its dissolved salts, is conductive enough to carry these induced currents, creating electromagnetic signatures that propagate through ocean basins, affecting the entire marine electromagnetic environment during geomagnetic storms. These oceanic electromagnetic variations are subtle, not strong enough to directly affect marine life in any obvious way, but they're real, measurable, evidence that auroral influences extend beyond atmosphere and land into the oceans, that the electromagnetic effects of space weather permeate every conductive medium on Earth's surface. Submarines can detect these variations, that use them as one more signal in the complex electromagnetic environment they navigate through. Marine animals that use electromagnetic sensing, sharks, rays, some bony fish that can detect electric fields, might perceive these auroral-induced fluctuations, though whether they can distinguish them from natural oceanographic electromagnetic noise is unclear. The aurora touches not just sky and land but water too, extending its electromagnetic reach to the depths, to environments that seem completely removed from polar light shows, but that nonetheless connected through the conductive pathways of seawater and Earth's crust. It's another reminder of how pervasive electromagnetic influences are, how auroral currents flowing hundreds of miles overhead can induce responses in seawater hundreds of miles away, how the entire planet participates in electromagnetic events, even when only the polar regions show visible manifestations. The aurora is more than a light show. It's a planetary-scale electromagnetic event, touching every conductive pathway, inducing currents in unexpected places, demonstrating that space weather affects the entire Earth system, not just the immediate vicinity of the visible lights. Scientists discovered in 2017 that certain auroral formations called dunes have spacings that match atmospheric gravity waves, parallel bands of light with regular spacing that reveal invisible wave patterns in the mesosphere. These dunes appear as rippled structures in the aurora, undulations spaced about 30 miles apart, extending for hundreds of miles, organized by atmospheric waves that are propagating through the mesosphere at auroral altitudes. Gravity waves, not to be confused with gravitational waves, are atmospheric waves generated by disturbances like mountains or weather systems, propagating upward through the atmosphere like ripples on water. When they reach auroral altitudes, they modulate the density and temperature of the air, creating periodic variations in atmospheric properties. And if an aurora happens to be occurring, the light production varies with these density modulations, creating visible bands that trace out the wave structure, making the normally invisible gravity waves apparent through their effect on auroral emissions. It's like how sound waves can be visualized by watching sand patterns on a vibrating plate. The waves themselves are invisible, but their effects create visible patterns in the medium. Auroral dunes are nature's way of visualizing mesospheric gravity waves, using particle precipitation as an indicator of atmospheric wave structure, connecting space weather to atmospheric dynamics in ways that wouldn't be apparent without detailed observation. And the discovery was recent, 2017, a reminder that auroral science continues to reveal new phenomena, that despite centuries of observation, we're still finding previously unrecognized patterns, still discovering ways that atmosphere and magnetosphere couple, still learning how to read the messages written in auroral light. The dunes were probably always there, appearing occasionally when conditions aligned. But no one recognized them as distinct phenomena until citizen scientists noticed the patterns and brought them to researchers' attention. Another example of how distributed observation by dedicated amateurs can contribute to scientific understanding. The probability of seeing auroras from any given location increases dramatically if you're willing to wait and watch for several hours rather than expecting immediate displays. Auroras are often intermittent, appearing and fading in cycles, brightening during substorms and quieting between them, creating a temporal pattern where patience becomes essential to success. You might arrive at a dark viewing location and see nothing, a quiet sky without obvious auroral activity, and assume there's nothing to see tonight. But if you wait, if you keep watching, then if you give the magnetosphere time to cycle through its processes, there's a reasonable chance that activity will intensify, that a quiet arc will brighten into curtains, that what seemed like an empty night will transform into an active display. The substorm cycle operates on timescales of hours, and catching the expansion phase requires either luck or persistence, either arriving at exactly the right moment or staying long enough that the right moment comes to you. This temporal requirement filters observers, separates those willing to commit hours to cold darkness from those seeking immediate gratification, creates a natural selection where the most memorable auroral experiences go to those patient enough to wait for them. And there's value in that waiting, in the meditation of cold darkness, in the act of watching sky for hours, in the discipline of sustained attention that modern life rarely requires. The aurora rewards patience, teaches that some experiences can't be rushed, that beauty often requires time to manifest, that the universe operates on its own schedule regardless of human convenience. Maybe this is part of the gift, not just the light when it appears, but the waiting that preceded it, the hours of darkness that make the emergence of colour meaningful, the patience that transforms observation into meditation, cold into communion with processes larger than ourselves. Some of the oxygen molecules that create green auroras were last excited by auroral particles months or even years earlier, residing in metastable states with extremely long lifetimes before finally releasing their energy as photons. These are called forbidden transitions, not because they're impossible, but because they're improbable under normal conditions, occurring only in the near vacuum of high altitude, where molecules can remain in excited states for extended periods without colliding with other molecules and losing their energy non-radiatively. The oxygen atoms creating tonight's green glow might have been excited last week, last month, last year, gradually radiating away their stored energy at timescales that seem impossibly slow compared to normal atomic processes. Most excited states last nanoseconds or microseconds before emitting photons, but forbidden oxygen transitions can last minutes, hours, longer, meaning that the green light you see tonight might be the delayed echo of particle precipitation that occurred long before you started watching, energy that's been stored in atomic states and is only now being released. It's like the sky has a memory, holding on to energy and releasing it gradually, creating a temporal smearing where past and present mix, where tonight's aurora contains contributions from yesterday's geomagnetic activity and last week's substorm. And this has scientific implications. It means that auroral emissions are not instantaneous traces of current precipitation, but include delayed components, making interpretation more complex, requiring models that account for atomic physics and metastable states and long relaxation timescales. But it also adds to the mystery, to the sense that auroras exist partially outside normal time, that they're conversations between past and present, that the lights overhead are partly historical. Delayed responses to events that occurred when the particles first arrived, but that are only now becoming visible. The aurora carries its own past within it, releases it gradually, makes history luminous. The exact mechanisms that accelerate particles to auroral energies along magnetic field lines are still debated by scientists. Still not completely understood despite decades of research and satellite missions dedicated to measuring the processes. We understand the general framework: magnetic reconnection, wave-particle interactions, field-aligned currents, but the detailed physics, the exact chains of causation, the specific conditions that determine which acceleration mechanisms dominate in which situations, all of this remains actively researched, still being refined, still generating new papers and satellite missions. Thus, as we know the outcome, particles arrive at auroral altitudes with specific energy distributions, creating observed auroral forms, and we know many of the processes involved, but connecting them into a complete quantitative model that predicts all observational details remains challenging. It's like knowing the plot of a story without catching every word of dialogue, understanding the general arc without being able to quote specific passages. The aurora tells us something is accelerating particles, but the exact conversational exchange between waves and particles, between fields and plasma, between different regions of the magnetosphere, that exchange remains partially opaque, interpretable, but not completely transparent. And this incompleteness is normal in science, actually. Most phenomena are understood in layers, from general to specific, not from qualitative to quantitative, with each layer of understanding revealing new questions, new complexities that require further investigation. We understand auroras vastly better than we did 50 years ago, orders of magnitude better than a century ago, but we're not done, not finished, not at the point where we can close the books and declare the problem solved. There are still mysteries in the magnetosphere, still questions about particle acceleration and auroral physics, still opportunities for discovery, still chances for the next generation of satellites and observers to reveal something we hadn't previously noticed. The aurora remains partially mysterious even as it becomes increasingly understood, holding on to secrets even while revealing others. Auroras influence the global electric circuit, in contributing to the electrical potential difference between Earth's surface and ionosphere, becoming part of a planetary electrical system that includes thunderstorms, fair weather fields, and ionospheric currents. Earth exists within an electrical environment, with the surface at one potential and the ionosphere at another, and current constantly flows between them, maintaining this potential difference through various processes including thunderstorms, which act as generators, and auroras, which modify ionospheric conductivity and current flow patterns. The global circuit connects all of Earth's electrical phenomena into one system, and auroras are participants, affecting how current flows in the polar regions, modifying the overall circuit resistance and voltage distribution, i.e. contributing to the electromagnetic environment that pervades the entire planet. It's like Earth is a vast battery with complex internal workings, and auroras are one component affecting its operation, one mechanism among many that maintain the electrical state of the atmosphere and ground. And this circuit has subtle effects on everything from cloud formation to atmospheric chemistry to possibly even biological processes in organisms sensitive to electromagnetic fields. We live inside this circuit, surrounded by electrical fields and currents we rarely notice, and auroras are visible manifestations of perturbations in this normally invisible system, moments when the circuit becomes bright enough to see, when electromagnetic processes that are always operating become temporarily visible through their light-producing effects. Here, the aurora is a window into planetary electricity, a demonstration that Earth is not electrically neutral but charged, potential-driven, conducting currents through its atmosphere and magnetosphere, maintaining fields and voltages that shape everything from weather patterns to space weather impacts. And understanding the global circuit requires understanding auroras, because they're major current carriers in the polar regions, significant modifiers of ionospheric properties, essential components in the planetary scale electrical system that operates continuously whether we notice it or not. During the solar storm of May 2024, auroras were photographed from all 50 US states, including Hawaii, bringing polar light shows to latitudes as low as 20 degrees from the equator, places where some of the oldest living residents had never seen such phenomena in their entire lives. Modern smartphones captured what would have seemed like miracles to earlier generations, lights that appeared in places where they hadn't been reliably documented in living memory, perhaps not for a century or more. The social response was remarkable. Millions of images flooded social media within hours, people sharing their disbelief and wonder, comparing notes on what they'd seen, creating a collective documentation of a rare event that previous generations would have experienced in isolation or small groups. The aurora became a shared moment, a common reference point across vast distances and diverse communities, something that briefly united people in simultaneous experience of cosmic beauty. And the technology that enabled this sharing, smartphones with increasingly sophisticated cameras, social networks that connect billions of people, also enabled the documentation itself, capturing colours and structures that many observers couldn't see directly with dark-adapted eyes, but that cameras revealed through long exposures and high sensitivity settings. The 2024 storm became one of the most photographed auroral events in history, not necessarily because it was the most intense. The Carrington event of 1859 was probably stronger, but because it occurred in an era when nearly everyone carried a capable camera and had immediate access to global communication networks. We documented the aurora collectively, built a shared archive of millions of images, created a historical record that's simultaneously comprehensive and redundant, and capturing the same event from countless perspectives, preserving it in ways that previous generations couldn't have imagined. And in doing so, we changed the nature of auroral experience slightly, making it both more public and more mediated, shared but filtered through technological capture and digital display. The mythology of nearly every culture within the auroral zones includes some explanation for the lights, from dragon breath to celestial warfare, from dancing spirits to divine messages, a testament to the human need to explain the unexplainable, to integrate extraordinary phenomena into coherent worldviews. Despite cultural differences spanning continents and millennia, despite completely different languages and belief systems and social structures, all of these cultures looked up at the same lights and created stories, developed explanations, built meaning around what they saw. And in a profound sense, all of those explanations were attempts at the same thing we're doing now with plasma physics and magnetohydrodynamics, trying to make the aurora comprehensible, trying to fit it into a framework of understanding, trying to transform raw sensory experience into knowledge. The mechanisms differ: myth versus science, narrative versus equation, but the impulse is identical. We cannot tolerate mystery without response, cannot simply watch lights in the sky without constructing explanations. The ancient explanations invoked the entities and forces that made sense within their cultural contexts: gods, spirits, ancestors, animals, warfare, all concepts that were real and meaningful within those worldviews. Our explanations invoke entities and forces that make sense within our context: electrons, magnetic fields, plasma instabilities, all concepts that are real and meaningful within our scientific worldview. Future cultures might look back at our plasma physics explanations the way we look back at Valkyrie shields and Firefox tails, not as wrong exactly, but as culturally contingent, as one way of making sense that reveals as much about the explainers as about the explained. The aurora remains the same, independent of our explanations, continuing its electromagnetic dance regardless of whether we attribute it to gods or particles or something we haven't yet conceived. And all the explanations, mythological and scientific, ancient and modern, are humanity speaking to itself about phenomena that exceed our immediate understanding, building bridges between what we see and what we believe, creating coherence in a universe that doesn't particularly care whether we understand it or not. Aurora research has practical applications for space exploration, helping us understand radiation environments that astronauts will face beyond Earth's magnetic shield, preparing us for journeys to the Moon, Mars, and eventually deeper into the solar system. The charged particles that create auroras when they hit Earth's atmosphere would hit unprotected astronauts in deep space, creating radiation exposure risks that need to be understood